Time is the silent river in which we all drift, carrying us steadily from one moment to the next. In a very real sense, each of us is already a time traveler. Every second, we slide 1 second into the future. Yet, when we close our eyes and imagine true time travel, we dream of more than this slow, one way journey. What if we could leap years ahead in a single night, or slip back to eras long past? Humans have wondered about such possibilities for millennia. Ancient myths and modern science fiction alike are filled with tales of journeys to yesterday and tomorrow. These dreams persist because, incredibly, science does not entirely rule them out. While no one has ever built a functioning time machine, physicists have uncovered theories suggesting that under the right conditions, time travel might be possible. Some involve traveling to the far future by moving at unimaginable speeds or skimming the edge of a black hole. Others hint at hidden cosmic loopholes, tunnels through space-time, or cosmic vortices that could send a daring traveler to the past. All of these ideas remain speculative and challenging, often requiring technology or energy far beyond our current reach. But pondering them opens our minds to the true nature of time and reality. In this journey, we will explore time travel theories that could actually happen according to our best understanding of physics. Each concept will unfold gently, with a calm and reflective tone, as if told in a late night story. We will visit speeding starships and strange wormholes, cosmic strings and rotating black holes, quantum experiments, and parallel worlds. Along the way, we'll also confront the paradoxes that plague time travel and the ways science imagines resolving them. This is a long voyage through thought and possibility, over 3 hours of quiet, mind expanding exploration. So settle in, make yourself comfortable, and let your imagination drift across the currents of time. Our first stop is the simplest trip to the future, achievable with nothing more than speed and the physics of Einstein. Racing into the future, relativity and time dilation. Imagine stepping aboard a spaceship and leaving Earth behind, bound for a distant star. As the engines fire, you feel the ship surge forward, faster and faster. Soon you are traveling at an incredible fraction of the speed of light, so fast that the stars ahead appear to brighten and blur. Inside the ship, time feels normal. You breathe, think, and age at the usual pace. But when you eventually turn around and come home, you make a startling discovery. Perhaps only a few years passed for you on your high-speed journey, yet decades or even centuries have passed on Earth. Your friends have grown old or are long gone, and the world you knew has changed. In effect, you leapt into the future. What you experienced was not magic or fiction, it was time dilation, a real effect predicted by Einstein's theory of special relativity and confirmed by experiments. According to relativity, time is not absolute. It is intertwined with space and can be stretched or compressed depending on motion. The faster you move through space, the slower you move through time relative to someone standing still. In our everyday lives, moving cars or airplanes barely make any difference in the flow of time. But at speeds approaching the cosmic speed limit, the speed of light, time dilation becomes dramatic. If you could travel at 99.9% of light speed, time would slow to a crawl for you compared to Earth. In fact, according to one calculation, a journey lasting 1 year on a ship moving at 90.999%, the speed of light would correspond to 223 years passing back on Earth. In other words, you would effectively jump over 2 centuries into the future by the time you returned. This scenario is often illustrated by the famous twin paradox thought experiment. Imagine identical twins. One remains on Earth while the other embarks on a high speed space voyage. When the traveling twin returns home, she finds that her earthbound sibling has aged far more than she has. To the traveling twin, only a few years might have passed aboard her fast moving spacecraft, while the stay at home twin experienced decades. This is not truly a paradox, but a consequence of how motion affects time. In reality, it has been indirectly demonstrated with precision clocks and real astronauts. For example, astronaut Scott Kelly spent 520 days aboard the International Space Station, moving at around 28,000 kilometers relative to Earth, while his twin brother Mark Kelly stayed on the ground. The effect on aging was minuscule but measurable. Scott aged slightly less, widening the age gap with his twin by a few milliseconds. At the speeds our current spacecraft travel, time dilation is tiny, mere fractions of a second. But the principle is clear. Given sufficient velocity, one can travel into the future faster than those left behind. Drifting through space at near light speed, watching clocks slow and hearts beat languidly, would be a surreal experience. To the traveler, nothing seems amiss. Time always feels normal in your own frame of reference. It's only upon comparing clocks with an outside observer that the difference emerges. This teaches us a profound lesson. Time is not a universal constant, ticking the same for everyone. Instead, it bends and stretches with motion. Nature's speed limit, the speed of light, about 300,000 kilometers per second, is also a kind of time limit. As you approach it, time effectively freezes relative to slower worlds. If it were possible, though it isn't according to relativity, to actually reach the speed of light, time for the traveler would stop entirely. You could cross the galaxy in an instant of your own time, but the rest of the universe would age millions of years in the meantime. Traveling into the future by high speed is, as far as we know, the only guaranteed form of time travel allowed by physics. It has been called a one-way ticket. You can go forward, never backward, and you cannot return to your starting era without even more exotic tricks. Importantly, this kind of time travel doesn't violate any known laws of nature or causality. It has been experimentally verified on small scales with particles and clocks, and observed in technologies like GPS satellites, which must account for time dilation to give accurate positions. Every time you use GPS navigation, in fact, you are subtly benefiting from relativity. The satellite clocks tick a bit faster due to being higher in Earth's gravity and a bit slower due to their orbital speed, requiring adjustment so they stay synced with ground time. The idea of journeying far into the future by going fast has a poetic simplicity. No fancy machines or cosmic phenomena are required, just speed. In principle, a sufficiently advanced spacecraft could take humans hundreds or thousands of years ahead. Imagine leaving Earth for what feels like a 5 year research mission near light speed and coming back to find the year 3000 unfolding below your ship's wings. The Earth would have moved on without you, history advancing while you skipped over it in the silence of space. It's a melancholic prospect. Everyone you knew would be gone, and society transformed in unforeseeable ways. This one way nature of relativistic time travel to the future carries a built in poignancy. Science fiction stories like Planet of the Apes and Interstellar have explored this feeling. Characters leave and return to an estranged future world. Unlike purely fictional time machines, though, relativistic time travel is firmly grounded in reality. It tells us that the flow of time is not immutable. Under extreme conditions, time itself becomes a flexible dimension we can stretch. As you lie back and contemplate this, consider the quiet irony. To visit the future more quickly, you must abandon the present and speed away, effectively missing out on the intervening time. Perhaps somewhere out in the cosmos, far off civilizations have already undertaken such journeys, leaping forward to see what becomes of their worlds. Or perhaps one day, human explorers will set sail on relativistic voyages, knowing they are saying goodbye to their own era forever to catch a glimpse of what lies ahead. For now, we remain bound to the slow current of time, but the door to the future stands open, written into the equations of space-time. We need only build the ships to sail there. Before we set our sights on more speculative time machines, let's explore another Einsteinian pathway to the future, one that requires not speed, but gravity. Instead of racing forward in a rocket, we will drift into a deep gravitational well, the realm of massive stars and black holes, and see how gravity itself can bend time's flow. Gravity's grip on time, slowing clocks near a black hole. Picture a lone astronaut orbiting a massive black hole at the edge of space. From a safe distance, she stares into the darkness of the black hole's maw, where light itself struggles to escape. Her spaceship is caught in a fierce gravitational field, a pit in space-time created by a colossal mass. As she circles this cosmic abyss, strange things begin to happen with time. Her onboard clocks tick slower compared to those far from the black hole. Every heartbeat, every second on her ship is stretched out. After what she experiences as only a few hours skimming the black hole, she fires her engines and breaks away to return home. To her astonishment, she finds that years have passed in the outside universe while she orbited in that strong gravity. Once again, she has effectively time traveled into the future, all because gravity warps time in much the same way motion does. This phenomenon is called gravitational time dilation, and it emerges from Einstein's theory of general relativity. According to the theory, time runs more slowly in stronger gravitational fields. Clocks closer to a massive object tick at a gentler pace than those farther away. On Earth, the effect is minuscule. A clock at sea level, closer to Earth's center, ticks just a tiny bit slower than one on a mountaintop due to Earth's gravity. But near an extremely massive and dense object, like a neutron star or black hole, the effect becomes very pronounced. In the thought experiment above, we considered a black hole. the ultimate warp in space-time. The supermassive black hole at our galaxy's center, Sagittarius A, contains the mass of 4 million suns crushed into a point. If you could orbit close to such a beast without falling in, time would slow dramatically for you. One example given by physicists: orbiting the Milky Way's central black hole, you might experience only 5 years, while 10 years pass in the rest of the galaxy. Half your decade would effectively disappear, slipped into the future beyond your ship's horizon. A more gentle version of this happens to astronauts on the International Space Station as well. They are slightly farther from Earth's center than people on the ground, so gravity is a tad weaker up there, and their clocks tick a bit faster than Earth clocks, counteracting the slowing from their orbital speed. The net result is that astronauts age just a little less than we do, though again, only by milliseconds or less. We have to account for gravitational time dilation in technologies too. As mentioned earlier, GPS satellites high above Earth tick faster relative to ground time, and engineers adjust them by about 45 microseconds per day to match Earth's clocks. Otherwise, your navigation would quickly drift off course. These are tiny shifts, but they confirm that gravity affects time in a measurable way. Now, black holes take gravitational time dilation to an extreme. The closer you approach the event horizon, the point of no return around a black hole, the more time stretches out. If you tried the risky maneuver of dipping near a black hole and then escaping, you could leap far into the future. This idea was depicted in the movie Interstellar, where astronauts visit a planet near a black hole and find that hours spent there translated to many years on Earth. The physics in the film was inspired by real calculations. Time dilation near a supermassive black hole can indeed make hours become years from another frame of reference. The catch, of course, is surviving such an encounter. The forces near a black hole are deadly. Tidal gravity, the difference in gravity between your feet and head, can stretch and spaghettify objects, and intense radiation might bombard any ship that ventures too close. In our musings, we imagine an astronaut with a sufficiently strong vessel and an orbit just distant enough to avoid destruction. Even then, there is an eerie thought. If she did drop all the way in, to an outside observer, she would never be seen to fully vanish. Instead, her clock would appear to slow and almost halt at the horizon, a frozen moment at the edge of time. For the astronaut herself, time would continue normally until, in classical theory, she is torn apart by gravity. But some speculative ideas suggest if the black hole is of a special kind, like a rotating Kerr black hole, falling through might not mean destruction. We will explore that possibility in a later chapter. For now, sticking to safer territory, we see that both motion and gravity allow travel into the future. Neither method lets you return to your past. They only alter the rate at which you move forward in time. They also have practical limits. To see a dramatic effect, you need either a travel speed very close to light or a proximity to an extremely strong gravitational field, conditions far beyond our current capabilities. However, these are not forbidden by physics, just technically challenging. If humanity survives far into the future, we might find ways to send travelers on near light speed voyages or to observe time dilation near black holes, perhaps via probes or messages sent through such regions. The idea of using gravity to time travel has a natural limit. You cannot go back in time by simply orbiting a massive object. You can only pause your own clock relative to the outside world. To an outside observer, you're delaying your progression through time, effectively hibernating near a gravity well while the cosmos moves on. In a sense, it's akin to an extended form of sleep or suspended animation, except accomplished through physics rather than biology. This invites a comparison. Science may one day achieve long term hibernation or cryogenic sleep for space travelers, another way to skip into the future by sleeping through decades. Both methods achieve a similar end, arriving in the future unchanged, though one is technological/biological and the other relativistic. In the stillness of night, thinking about these concepts can be strangely comforting. Time, which normally feels so rigid, ticking away second by second, is revealed to be flexible. The universe holds loopholes that let us gently bend the flow of time to our advantage. If you were to float in a safe orbit around a black hole, watching galaxies spin slowly in the far distance, you could take a kind of shortcut to the future. It's a one-way trip, yes, but it reminds us that the cosmos is full of marvels that challenge our common sense. As we drift through these reflections, let's prepare to leave the relatively solid ground of Einstein's well tested relativity and venture into more exotic territory. Our next topic moves beyond natural effects to theoretical constructs, objects, and phenomena that scientists have hypothesized might allow time travel both to the future and the past. We'll start with one of the most intriguing ideas of all: wormholes, the hypothetical tunnels through space and time. Wormholes, cosmic tunnels through time. In a quiet laboratory, or perhaps a far flung corner of space, imagine stumbling upon a shimmering portal suspended in midair. It looks like a hole in the fabric of reality, a tunnel wreathed in swirling light. With a deep breath, you step through and find yourself emerging not just in a different place, but in a different time. Perhaps you walk out into the world decades earlier or centuries later. This fanciful portal is known as a wormhole, a concept that has captured the imagination of scientists and writers alike. Wormholes are a staple of science fiction, from Stargate to Interstellar, often serving as convenient shortcuts across space and time. But could they exist in reality, and could they truly allow time travel? According to general relativity, wormholes are not forbidden by the math. They are theoretical solutions of Einstein's equations that connect to two distant points in spacetime. In essence, a wormhole can be visualized as a tunnel with two mouths, each mouth opening into a different location and possibly a different time. If one could traverse the tunnel, you might step out light years away from where you entered, and potentially years in the past or future. The idea of using wormholes for time travel was seriously explored in 1988 by physicist Kip Thorne and colleagues, partly inspired by a call from novelist Carl Sagan, who wanted a scientifically plausible method of interstellar travel for hit book Contact. Thorne and his team found out that if a wormhole could be held open and stabilized, it might be used as a time machine. The method would be to take one mouth of the wormhole and move it at high speed, or place it in a strong gravitational field, and then bring it back. Thanks to time dilation, the traveling mouth would age less than the stationary mouth. Once reunited, the two ends of the wormhole would no longer be synchronized in time. Entering the younger end would spit you out the older end at an earlier time. For example, imagine we create a wormhole in the year 2100, then take one end on a fast rocket at near light speed out into space and return it to Earth. Perhaps the traveling end has only aged 1 year, while the stay at home end aged 10 years. Then the mouth that traveled might be 9 years younger than the other. If in 2110 someone enters the younger mouth, they could emerge from the older mouth in the year 2101, effectively stepping 9 years into the past. This scenario avoids any single object exceeding light speed. The time difference arises purely from relativity and the wormhole's connectivity. It sounds incredible, a true time machine without overtly violating physics. But wormholes come with hefty caveats. First, we have no evidence that wormholes actually exist in the universe. They remain a hypothetical construct. General relativity allows them in theory, but that doesn't mean nature has built any. If they do exist, they might be tiny. Some theories speculate that microscopic primordial wormholes could have formed in the early universe, extremely small, perhaps around 10 world 33 centimeters across. Such a tunnel would be too small for a person, or even an atom, to traverse. To be usable, a wormhole would need to be enlarged or engineered somehow, and that leads to the second caveat: stability. Wormholes, if they exist, tend to be unstable. They could pinch off or collapse if anything tries to go through. The equations suggest that to keep a wormhole open, exotic matter with negative energy might be required to counteract the tunnel's natural tendency to close. Negative energy isn't science fiction. Quantum physics allows for small regions of negative energy density. The Casimir effect is an example. But accumulating and controlling enough of it to shore up a macroscopic wormhole is far beyond current technology. Interestingly, there has been recent theoretical work indicating wormholes might be more traversable than previously thought. For instance, one 2021 study by physicist Pascal Coiron used an alternative formulation of the black hole equations, the Eddington-Finkelstein metric, to show that a particle could traverse a wormhole without encountering infinite forces. This challenges earlier analyses that found wormholes would instantly collapse if something tried to pass through. If Coiron's results hold, they are theoretical for now. It could imply that a carefully constructed wormhole might allow safe passage. Even so, we remain in the domain of hypothesis. Stephen Hawking once wryly noted that a good reason to doubt backwards time travel via wormholes is the lack of tourists from the future showing up in our time. Wormholes might be possible on paper, but using them as time machines could be thwarted by other physics we don't yet understand, or simply by their rarity. Let's indulge the idea a bit further, though. Suppose in a far future, humans, or another species, figure out how to create or find a stable wormhole. They turn it into a time portal. The catch with such a portal is that you likely cannot go back to a time before the wormhole existed. In our earlier example, no one could use that wormhole to visit Earth before 2100 because that's when the wormhole was first created. This seems to be a general rule. Most time machine mechanisms, including wormholes, would be constrained such that you can't reach an era earlier than the machine itself. So, time travel wouldn't let you wander arbitrarily through all of history, just between the points where a stable wormhole or time path has been established. Another possible limitation comes from quantum effects. Some researchers think that quantum fluctuations would build up and destroy a wormhole if you try to use it for backwards time travel. Kip Thorne and his colleagues found signs that as soon as a wormhole time machine is activated, feedback from vacuum energy, like a runaway loop of light, spontaneously appearing and intensifying, might blow it up, in line with Hawking's chronology protection conjecture. In other words, the universe might protect itself from causal paradoxes by destabilizing time traveling wormholes. We'll discuss that conjecture more later, but it's fascinating to think the laws of physics might have built in safeguards, like a fuse burning out to prevent a dangerous circuit. For now, in our relaxed journey, imagine the gentle wonder of a wormhole that does function. What might it feel like to step through one? Perhaps like walking into a misty tunnel where light bends in strange ways and emerging into a different sky under alien stars. If it connects different times, you could literally walk into yesterday or tomorrow. The world on the other side might be the one you know, but at a different stage, your hometown a century ago with dirt roads and horse carriages, or centuries in the future with towering new buildings or unfamiliar technologies. Because wormholes can also connect distant places, you might travel not just in time, but in space, say from Earth to a far planet, and from the year 2500 to the year 3000 in one step. The possibilities are limited only by how the tunnel mouths are configured. Throughout all this, a crucial point to remember is that wormholes remain speculative. They illustrate how flexible Einstein's spacetime can be, that it might fold and connect in unexpected ways. Whether nature allows such convolutions at macroscopic scales is an open question, but wormholes give us a valuable mental image that time and space might be far more connected than our normal experience suggests. In a very real way, relativity tells us space and time are two sides of the same coin, space time, so a shortcut through space is also a shortcut through time. As we ponder wormholes in the soft darkness of a sleepless night, we tap into the profound idea that the past and future might be out there, not gone or yet to be, but existing in different corners of a grand tapestry, corners that perhaps with immense effort we could reach. Next, we'll explore another striking theory for time travel that emerged in the 20th century. This one doesn't rely on hypothetical tunnels, but on something almost as fantastical, enormous, nearly incomprehensible cylinders and the twisting of space-time by rotation. It's time to meet the Tipler cylinder, a peculiar and ambitious time machine proposal. The Tipler cylinder, spinning back the years. Imagine a cylinder as long as a planet, or even effectively infinite in length, composed of ultra-dense matter. Now set this gigantic cylinder spinning, faster and faster, billions of revolutions per minute. The space around it begins to twist like taffy being stirred. Any object that ventures close to the spinning cylinder finds the fabric of space-time itself being dragged around in circles. In this whirling space-time, a clever spacecraft can plot a particular spiral course around the cylinder and end up arriving before it departed. This is the essence of the Tipler cylinder, one of the most famous theoretical time machines derived from general relativity. The Tipler cylinder idea was published by physicist Frank Tipler in 1974, though it builds on earlier work, solutions found by Willem van Stockum and Cornel Langsos decades prior. Tipler showed that a rotating cylinder of sufficient size and density could create what physicists call closed time-like curves, or CTCs. A closed time-like curve is basically a path through space-time that loops back on itself in time, returning to the starting point at an earlier moment. In simpler terms, it's a world line, a history of an object that forms a closed loop. If you travel along such a loop, you would return to your own past. In Tipler's proposal, the rotation of a huge cylinder would literally drag space-time around with it, an effect known as frame dragging. If the rotation is extreme enough, it tilts the light cones of objects, the directions in space-time a particle can travel, so that part of an object's future path can loop into its past. A spaceship following the right trajectory around the cylinder could find itself in a previous time period when it completes its journey. This concept, while mind-bending, arises from valid equations of general relativity. However, the practical requirements are staggering. Tipler's analysis indicated that for this to work, the cylinder probably needs to be infinitely long. An infinite rotating cylinder is not exactly something we can construct in reality. Tipler did speculate that a very long finite cylinder might also work if spinning fast enough, but that was not definitively proven. Even if finite, the cylinder would need to be incredibly massive. One suggestion described matter 10 times the mass of the Sun, compressed into a long, dense form. The Anderson Institute, a private research group fascinated by time travel, colorfully describes such a cylinder as a black hole that has passed through a spaghetti factory. The cylinder would have to rotate at billions of RPMs to create the needed frame dragging. The engineering and energy requirements of this are beyond enormous. They are, for all intents and purposes, impossible with any foreseeable technology. Moreover, Tipler's solution is a vacuum solution in general relativity, meaning it's mostly a mathematical spacetime with the cylinder not accounting for other matter. Introducing realistic conditions might spoil the effect. Stephen Hawking raised an important objection. Even if you could build such a machine, general relativity may forbid it unless exotic matter with negative energy is present. In a 1992 paper on the chronology protection conjecture, Hawking argued you can't create a time machine in a finite region without violating energy conditions. Essentially, you can't do it with normal matter. The Tipler cylinder, as originally conceived, doesn't involve negative energy. It tries to use normal mass and rotation. Hawking's reasoning suggests that if only normal positive energy is allowed, any attempt to set up CTCs, like a finite Tipler cylinder, will fail. This ties back into that idea that maybe physics prevents closed time-like curves from forming in any practical setup. All these caveats mean the Tipler cylinder probably cannot be built with known physics. But it's valuable as a thought experiment. It shows that rotating spacetime can produce time loops. Interestingly, frame dragging is a real effect. Earth's rotation drags spacetime a tiny bit, observed by the gravity probe B experiment. A rotating black hole, Kerr black hole, drags spacetime a lot near its horizon. In fact, the Kerr black hole solution of general relativity also contains closed time-like curves inside the spinning singularity region. Of course, entering a black hole interior is a one-way trip and likely fatal, but it's notable that rotation often opens the door to weird causal structures in the equations. Now let's imagine for a moment that a Tipler cylinder could be made, perhaps by an extremely advanced civilization. How might one use it? Likely, you'd place a spaceship near the cylinder and follow a very specific spiral path as it rotates. You'd feel the tug of an incredible gravitational and inertial force as space-time swirls. It might be a rather turbulent ride, but as you circle around, you start noticing that stars ahead of you are shifting to earlier positions, and the clock on your ship might show anomalous readings. Completing the loop, you head back to your starting point, but find the calendar reads an earlier year than when you launched. Perhaps you left in 2500 and have now arrived in 2490. The cylinder would have effectively flung you backwards a decade. Remember the limitation, though. Similar to wormholes, you probably couldn't go back to a time before the cylinder was constructed or set spinning. The time machine might only allow travel to as early as when it became operational. Also, any small error in your trajectory could mean you don't achieve the loop correctly, or worse, you crash into the massive cylinder, which would be catastrophic. This time machine, if it existed, would be a gigantic, dangerous piece of infrastructure, not a cozy DeLorean car or a phone booth. It underscores how strange and extreme the conditions for time travel are in physics. We're talking about manipulating astronomical masses and relativistic rotations, not just flipping a switch on a gadget. Lying back and contemplating the Tipler cylinder, one can't help but marvel at how unintuitive the universe can be. Who would think that simply spinning something could twist time into a loop? It's as if time were a ribbon that can be wound around a spindle given enough force. The Tipler cylinder also invites philosophical thoughts. If one could travel back along a loop, what happens to free will and causality? Could you alter events, or would you be trapped in a self-consistent loop? Tipler's solution itself doesn't answer those questions. It just shows the path is there. The universe might still enforce consistency, Novikov's principle, which we'll address later, or spawn alternate timelines. But before jumping into paradoxes, let's explore a few more proposed mechanisms of time travel. The cylinder isn't the only game in town. Another idea involves the very fabric of the cosmos, hypothetical defects in space called cosmic strings. Cosmic strings, threads that weave through time. High in the void of space, imagine two impossibly long, thin strands, cosmic strings, zipping past each other at nearly the speed of light. These strings are narrower than an atom, yet incredibly dense, carrying titanic mass and tension. As they whip by, the space around them warps dramatically. Now, picture a daring spacecraft timing its route to loop around the intersection of these strings. If executed perfectly, the ship could emerge at an earlier time than it departed. This scenario describes a time travel mechanism proposed by physicist J. Richard Gott in 1991 involving cosmic strings. Cosmic strings are theoretical objects thought to be relics of the early universe. Essentially, they are like fault lines or cracks in space-time that might have formed as the universe cooled after the Big Bang. They are not related to string theory, despite the name. Rather, they are a kind of topological defect. If they exist, each cosmic string could be incredibly long, potentially stretching across galaxies, and have immense mass, causing gravity to warp around them. Gott realized that if you have two cosmic strings passing by each other at high velocity, their gravitational fields and the motion combined could create a region where time loops are possible. The key is that moving cosmic strings could bend spacetime enough to permit closed time-like curves, much like the Tipler cylinder, but perhaps not requiring infinite length in the same way. In Gott's scenario, a spaceship traveling in a particular trajectory around two cosmic strings could end up arriving before it left. One way to picture it, the two strings create a kind of cone-shaped distortion in spacetime. If they move just right, they effectively drag spacetime around in a way that if you loop around them, you can come back on the other side of the cone in the past. It's akin to finding a shortcut on a Mobius strip-like structure of spacetime. Importantly, like with wormholes and Tipler cylinders, you can't go back to a time before the cosmic strings set up this configuration. The time machine becomes active only once the strings are in position and moving. What would it take for this to work? The energy involved is enormous. By some estimates, to bend by even 1 year using cosmic strings, the strings would need to contain on the order of half the mass energy of an entire galaxy. This is an almost inconceivable amount of mass. Essentially, you'd need to harness something like half of all the stars in a galaxy and put that energy into your cosmic strings. And you'd need two of them moving at near light speed. It's safe to say this is not a technology we'll have any time soon, if ever. Moreover, to date we haven't confirmed that cosmic strings exist. We have some observational constraints. If they existed in large numbers or with certain strengths, they'd affect cosmic microwave background or gravitational waves in ways we might detect. So far, nothing conclusive has shown up. They remain a hypothesis. Still, the cosmic string idea is fascinating because it doesn't necessarily require exotic negative energy matter. It uses normal mass, albeit an astronomical amount, and relativity. It's another example of how extreme configurations of matter might produce time loops. Gott's paper on this was one of the early serious publications on time travel in reputable journals shortly after Kip Thorne's wormhole work. It helped spur scientific dialogue on whether time travel is strictly forbidden or might be allowed in certain weird space-time geometries. In 1992, there was even a conference of physicists discussing time travel, partly due to interest in these new models. If we think imaginatively, one might wonder, could an advanced civilization ever utilize cosmic strings? Perhaps not by literally finding two strings and moving them. That seems beyond godlike, but maybe by creating analogous conditions. To create a closed time-like curve with cosmic strings, you need tremendous gravitational fields moving rapidly. Conceivably, a sufficiently advanced technology could mimic that effect with artificial constructs. This veers into realms we can hardly speculate about. In any case, cosmic strings as a natural phenomenon might themselves be cosmic curiosities. If one passed through our solar system, for instance, it could cause strange gravitational lensing effects or even tiny time distortions. We'd be wise to keep an eye out for any hints of such objects, because they would teach us new physics. For the purpose of our relaxing journey through thought, envision floating near one of these cosmic strings. It would be invisible to the eye, except perhaps for the way it distorts the stars behind it, like looking through a thin cylindrical lens. If two strings came by, you might see space twist in a peculiar dance. Perhaps you'd witness multiple images of stars or galaxies as light bends around the moving strings. Time itself would be malleable in their presence. The concept of looping around them and coming out at an earlier time challenges our ordinary idea of cause and effect. It's like finding a hidden circular path in the river of time that loops back upstream. Just as with the Tipler cylinder, any use of cosmic strings for time travel would raise questions. Could you change history on your loop, or would everything somehow self consistently fit? We'll delve into those questions soon. But first, we have a few more theoretical time travel proposals to cover, including ones involving black holes and faster than light travel. Each new idea adds a layer to our understanding of what might be possible and why it might be prevented. For now, let the image of those cosmic strings imprint on your mind, thin, powerful threads, remnants of creation, potentially capable of sewing together the fabric of time itself into a loop. In the vast quiet of space, if such things exist, they would silently warp reality around them. Our next topic takes us back to black holes, but a special kind known as a Kerr black hole, which might just provide a natural time portal if entered under the right conditions. Spinning black holes and ring singularities, a passage through time. Deep in space, a massive star collapses under its own weight, shrinking and spinning faster and faster. Instead of forming a simple spherical black hole, it becomes a rotating black hole, known as a Kerr black hole. At its center, general relativity predicts not a point singularity, but a rotating ring. Now imagine an intrepid explorer plunging into a Kerr black hole. Instead of being crushed at a central point of infinite density, she slips through the ring singularity. In theory, passing through that ring could eject her into an entirely different region of space-time, perhaps a different time, or even a different universe altogether. On emerging, she might find that she has traveled into the past or future relative to where she began. This speculative scenario arises from the mathematical solution Roy Kerr found in 1963 for rotating black holes. A Kerr black hole's rotation creates a frame dragging effect, much like Tipler's cylinder, but naturally occurring. Inside a rotating black hole, there are regions where time and space coordinates can mix in strange ways. The Kerr solution implies the existence of an ergosphere, an area outside the event horizon where space is dragged around, and two event horizons instead of one. Most intriguing is that ring singularity. If you could avoid the deadly gravitational forces, the equations suggest it could act like a portal. One might pass through the ring and avoid hitting infinite density, potentially popping out through a hypothetical white hole, the time reverse twin of a black hole that expels matter and light. The idea of white holes has been around a long time, but none have ever been observed. They are allowed in the math of relativity, but if they exist, they'd be peculiar, essentially an outflow where nothing can enter from the outside. If a Kerr black hole connects to a white hole, that begins to sound like a wormhole. Indeed, some have hypothesized that a rotating black hole might provide a natural wormhole of sorts. Unlike the wormholes discussed earlier, which typically require exotic matter to hold open, a Kerr black hole's interior structure might create a tunnel due to how it warps spacetime. However, whether one could actually survive a trip through is dubious. There are indications that the Kerr wormhole, if we call it that, would be highly unstable. The moment any matter tries to go through, it could cause the passage to collapse, or the traveler to inevitably hit destructive regions. Also, quantum effects are not accounted for in the classical Kerr solution. A real rotating black hole likely still has something akin to a singularity or at least extremely lethal conditions. But let's indulge the classical picture for the sake of exploration. Roy Kerr's analysis provided the first realistic, non spherically symmetric black hole model, and it tantalizingly suggested time machine possibilities. If you fell into a precisely rotating black hole and navigated to the ring singularity, you might avoid being spaghettified, stretched by gravity due to centrifugal force balancing it out. Passing the ring, you could potentially enter another patch of space-time, which might be another time or place. Some interpretations are that this could lead to travel into the past, a one-way trip, since you probably can't get back. It's often said as a warning that a wild Kerr black hole, if entered, gives no telling about where or when you'd emerge. It could be an entirely different universe's past or future. Science fiction has toyed with this. The idea that black holes might be gateways, like in Interstellar, though in that film the portrayal involves additional interventions by higher dimensional beings to make it survivable. Astrophysicists generally agree that diving into any black hole, spinning or not, would be fatal with our known physics. The gravitational tides would rip you apart, and even before that, intense radiation from infalling matter or vacuum polarization might fry you, not to mention the very act of interacting might destroy the supposed portal. Stephen Hawking famously pondered these issues, concluding that time machines, like one made from a black hole wormhole, probably self destruct upon activation. Again, the chronology protection idea. Nonetheless, Kerr black holes broaden our view of what relativity permits. They show that rotating gravity fields can do even crazier things than non rotating ones. The line between a wormhole and a spinning black hole becomes thin in theory. If somewhere in the universe there exists a naturally occurring naked Kerr singularity, meaning not hidden behind an event horizon, which cosmic censorship conjecture says shouldn't happen, it could be a natural time travel device. However, Cosmic censorship suggests all singularities come with horizons, preventing external observers from seeing the singularity or using it like a portal in an accessible way. The Kerr solution technically has a region one could exploit if it were exposed, but realistic conditions likely cloak it. Imagining the experience, falling into a Kerr black hole might be less like being sucked into a point and more like being whipped around a whirling funnel. You'd see space and time distort bizarrely. Perhaps you'd witness external clocks speed up or slow down unpredictably as you approach the ring. Crossing the ring, if possible, you might perceive a flash or a topological weirdness, then suddenly find yourself spat out in a different cosmic scenery. The silence of space returns, but star constellations look unfamiliar. Checking your instruments, you realize the date doesn't match anything sensical relative to where you came from. You have either gone far into the future or far into the past, or you might not even be in the same universe. It's a lonely thought, a one-way trip through a cosmic doorway with no guarantee of return or even survival. This is clearly more science fiction at this point than an actionable plan. But what's important is that nothing in the equations strictly forbids the Kerr time travel loophole. It's the practical and quantum considerations that likely shut it down. In our quest for time travel theories that could actually happen, rotating black holes are on the fringe. They're a maybe, hanging on whether new physics, quantum gravity, allows or disallows them as portals. If future understanding of quantum gravity, say via string theory or loop quantum gravity, reveals that black hole interiors connect to other points in time that would revolutionize our concept of cause and effect. For now, as you listen to this in a relaxed state, think of the Kerr black hole as a reminder of nature's complexity. Something as simple as a rotating mass, taken to an extreme, could fold space and time into a carousel where stepping off puts you back before you got on. It resonates with the Tipler cylinder and cosmic strings, rotation, and massive energy density enabling temporal tricks. Perhaps the universe has a symmetry or pattern we haven't fully grasped, or under special conditions, time wraps around on itself. If so, it might be nature's hidden design, waiting for an explorer brave or foolish enough to test it. Until then, we keep these ideas in the realm of mathematical imagination. Now, shifting from gravity-based proposals, let's examine another category of time travel notions, those involving faster-than-light travel. As we'll see, in Einstein's relativity, faster than light inevitably ties into backwards time travel. Concepts like hypothetical particles, called tachyons or warp drives, fit here. Could going superluminal, faster than light, allow us to cheat time? Let's explore that next. Faster than light dreams, tachyons, and warp drives. For as long as humans have been shooting for the stars, we've bumped up against a frustrating limit. Nothing can be accelerated to the speed of light, according to relativity. But what if there were ways to break that limit? Science fiction is rife with ideas like hyperspace jumps, warp drives, or particles that always go faster than light. The tantalizing aspect of these notions is that they imply time travel to the past. As a consequence of relativity, any faster than light, FTL, signal, or object can lead to causality violations, meaning you could send information or travelers back in time. Let's unpack this gently. Relativity has a well known quirk. The order of events can become flipped in different reference frames if something moves faster than light. For instance, imagine you have a device that can send a signal at FTL speed. In some other reference frame, a different state of motion, that signal could be received before it was sent. This isn't just speculation, it falls out of the Lorentz transformations that underlie special relativity. In essence, FTL travel implies a world where cause and effect can get jumbled, a recipe for time travel paradoxes. Thus, many physicists suspect that FTL is impossible precisely because it would allow time travel, which leads to logical problems. However, impossible hasn't stopped people from theorizing. Two concepts often mentioned are tachyons and warp drives. Tachyons are hypothetical particles that, instead of being stuck below light speed like us, with real mass, would always move above light speed and have imaginary mass in the math. They were proposed in the 1960s as a curious possibility in relativity theory. If tachyons existed, one could argue they are constantly traveling through time in some sense. They would appear to go backwards in time in some frames. Thankfully, or perhaps disappointingly, tachyons have never been observed. Most physicists consider them a mathematical curiosity. If they did exist, it's unclear if they could interact with normal matter in a controlled way or if they would just destabilize things. Warp drives are a more recent and popular idea. Inspired by Star Trek's fictional warp drive, physicist Miguel Alcubierre in 1994 found a solution in general relativity that, in theory, allows a bubble of space to move faster than light relative to distant observers. The idea is that you contract space in front of your ship and expand space behind it, effectively surfing a wave of bent spacetime. Within the bubble, you're locally not breaking light speed, so you avoid the immediate issue of infinite mass, but the bubble itself moves superluminally relative to outside. This concept was thrilling because it bypassed some traditional constraints. However, the original Alcubierre warp drive required negative energy, like wormholes do, to create the bubble, and a lot of it. Later calculations indicated the energy requirements, while enormous, might be somewhat reduced with certain modifications. But still, it's speculative and no known way exists to create or sustain a warp bubble. What's interesting is that if you had a warp drive, you would have to be careful because it could become a time machine. Certain analyses show that if you take a warp ship on a specific trajectory, you could arrive back before you left. Essentially, two colluding warp bubbles or a specific loop could allow closed time-like curves. This again shows the intimate link. Any method to exceed light speed opens the door to time travel. Stephen Hawking, always the skeptic of time travel, noted that even a warp drive likely would be forbidden or would destroy itself if used for backward time travel. To keep it relaxing, let's imagine what FTL travel would feel like without fretting too much over the physics. Suppose you're on a starship with a warp engine. You engage the drive, and space begins to distort. Distant stars suddenly shift. Perhaps a star that was light years away now appears just outside your window due to the contracted space. In a flash, you traverse tens of thousands of kilometers, then light years. From your perspective, the trip might seem almost instantaneous to a nearby star system. To outside observers on Earth, they see your ship vanish and reappear elsewhere faster than any light signal could have traveled. If you then turned around and came back similarly quickly, you might find you've returned before the light from your departure event even reached home. It could get stranger. Depending on how the frames align, you might even beat yourself back, so to speak, enabling bizarre scenarios where you see your own departure from afar. It's easy to see how paradoxes could arise. One could, in theory, send a message to the past or try to alter an event with FTL. Tachyons, if they were real and could send signals, would have similar issues. For instance, imagine two people with tachyon walkie-talkies. By moving relative to each other and sending tachyon signals, they could set up a loop that results in a message arriving before it was sent. These thought experiments strengthen the chronology protection mindset that nature conspires not to allow such things. Yet, none of this definitively proves FTL and time travel are impossible. It only shows they come as a package deal. Some speculative solutions involve theories beyond Einstein's. For example, certain quantum gravity or string theory ideas entertain extra dimensions or loopholes that could permit effective FTL without paradox, though usually there is a catch that saves causality, such as the need for those extra dimensions to have their own constraints. One concrete example: in 2011, an experiment Opera initially thought they detected neutrinos traveling faster than light, which caused a media stir about possible time travel. It turned out to be an error, a loose cable affecting timing measurements. But for a moment, it reignited debate about what if something could go FTL. The consensus remains that if anything truly can go faster than light, our understanding of causality would have to change. For the dreamers and the sci fi enthusiasts, warp drives remain a hopeful idea. A few researchers still publish papers refining the concept, sometimes claiming to reduce energy needs or eliminate the need for negative energy by clever tricks at the cost of other issues. It's a far shot, but not pure fantasy. It's rooted in real equations, just in regimes we can't attain. If one day warp drive experiments become possible, we might also have to face the reality of potential time travel. Perhaps any viable warp drive will come with built in limitations that prevent paradox. Maybe it can only go so fast, or requires a sequence that avoids loops. Or maybe, as Hawking humorously put it, the first time someone tries to activate a true FTL time loop, something catastrophic will occur: self destruction of the machine via feedback, etc. In the stillness of our nighttime reflection, the notion of FTL and time travel can be both exciting and unsettling. It's as if the universe holds out a tempting shortcut, yet guards it fiercely with logical booby traps. The ideas of tachyons and warp bubbles push us to imagine existence beyond our normal limits. They challenge us. If we could outrun light, would we outrun causality itself? And if so, how would the universe make sense of it? As we delve deeper, we realize we must address those very logical booby traps, the paradoxes of time travel. Up to now, we've mostly explored mechanisms by which time travel might occur. But what happens if it does? Would you be able to change the past? Would multiple timelines branch out? Or would nature prevent any contradictions from arising? In the next sections, we will gently examine the famous grandfather paradox and several potential resolutions to it, including parallel universes and self consistency. These are not exactly machines or physical theories, but they are theoretical frameworks that would allow time travel without breaking reality. Understanding them is crucial to any discussion of time travel that could actually happen, because without resolving paradoxes, true time travel to the past seems to make no sense. So, let's now turn to the mysteries of causality and see how physicists have wrestled with them. The grandfather paradox, when causality breaks down. A young time traveler steps out of her machine, arriving in a small town many decades before her own birth. She has a singular, dark purpose to prevent her grandfather from ever meeting her grandmother. Skulking through the streets, she eventually confronts her teenage grandfather to be. In a tragic moment, she causes his demise before he ever encounters her grandmother. Satisfied, she wipes her fingerprints and returns to her time machine, only to realize a logical catastrophe. If her grandfather died before fathering her parent, then she herself could never have been born. And if she was never born, who came back to commit the act in the first place? This self contradictory scenario is the classic grandfather paradox, the most well known time travel paradox of all. It highlights the core problem with time travel to the past, the possibility of changing history in a way that prevents the time travel from happening in the first place. The grandfather paradox is often phrased in violent terms, killing one's ancestor, but it can be any action that alters past conditions leading to a contradiction. For example, going back and destroying your time machine before you used it, or even something as mundane as leaving a note that prevents you from ever deciding to time travel. In each case, you get a loop of cause and effect that doesn't line up consistently. It's a headache for logic. Effect, your presence in the past, negates the cause, your origin or decision to time travel. When we discussed wormholes, Tipler cylinders, cosmic strings, etc., we implicitly assumed the traveler does not create a paradox. They might have gone back, but perhaps they were careful or fate intervened. But logically, if time travel is possible, somebody could attempt a paradoxical action. How could the universe cope? One simple answer is maybe it can't, and thus backwards time travel truly is impossible. This is essentially Hawking's viewpoint with the chronology protection conjecture that something will always prevent these situations. Another approach is to say, maybe the paradox only exists because we assume one unique timeline. If time travel creates or accesses alternate timelines, parallel universes, then there is no paradox. You killed a version of your grandfather in another universe, but not your original one. A third approach is the Novikov self-consistency principle, which suggests that if time travel occurs, events will always adjust to avoid a paradox. That is, you might try to kill Grandpa, but something will inevitably thwart you. Your gun jams, or you realize the man you thought was your grandfather was someone else, etc. In this view, timelines are self consistent loops. You are always part of history, and you never actually change the known past. Let's examine these resolutions one by one in a calm and reasoned way. They each turn the brain twisting paradox into a maybe manageable scenario. First, parallel timelines or the multiverse solution. This posits that when you travel back in time, you actually enter a different branch of reality, a parallel universe that is identical up to the moment you arrived, but then diverges. So, the moment you appear in 1950, say, to sabotage Grandpa's romance, you have split off a new timeline. In that timeline, your grandfather indeed will not bring about your parent, and thus you, in that branch, will never be born. But that you came from another branch, the original timeline, where history was intact up to the point you left. In the new branch, there might be a version of you that never exists, but the you who traveled is safely there to observe it all. Essentially, you have moved sideways into a copy of the past, not the actual past of your origin timeline. This is a consistent approach used in many sci fi stories. For instance, the Marvel movies' take on time travel, or the classic science fiction novel Timeline by Michael Crichton. It removes the contradiction because you're not affecting your own origin timeline. That remains back home, presumably now without you. Perhaps you vanished and never returned, or you returned to an altered future, but it's not the future, etc., depending on the rules. The downside of this solution is philosophical. You don't truly change your past, you create a new one. If your goal was to save someone in your timeline or prevent a war in your history, it doesn't help those in the original timeline. It just spawns a new branch where things are better or worse. Some find that less satisfying, as it means you can't actually fix your own past, only an alternate. Physicist David Deutsch has even formulated a version of quantum mechanics where closed time like curves lead to a mixture of states equivalent to many worlds, thus avoiding paradox by effectively distributing changes across consistent histories. Next, Novikov's self consistency principle. This idea, named after physicist Igor Novikov, asserts that if time travel to the past is possible, the only solutions that occur are those that are globally self consistent. In other words, you can't change the past because whatever you do was always part of history. Perhaps you did go back and meet Grandpa, but instead of killing him, something about your interaction actually ends up ensuring he meets your grandma. A famous whimsical example of a self consistent loop is the information paradox or bootstrap paradox. Suppose you travel forward in time and copy down a formula for a great invention, then come back and give it to a younger version of yourself or someone in the past. That invention gets developed, passed down, and eventually is the very thing you saw in the future. The information has no clear origin. It exists in a loop, but it's consistent. There's no contradiction. The story from the How Stuff Works article about the professor and student exchanging a theorem across time is exactly this kind of loop. The theorem was never independently created, it was passed along a circular timeline. This defies our usual understanding of cause. Where did the idea originally come from? But it doesn't produce a logical paradox in terms of events. In a self consistent timeline, you can't kill your grandfather because, simply put, you didn't in the history that led to you. If you go back, something will always intervene to preserve consistency. It might not even be mystical, It could be as straightforward as you change your mind or you miss the critical moment. Some research in physics has tried to model this with probabilistic rules. For example, there were studies, like one referenced by Wired in 2010, where physicists playing with time travel simulations found that if an event would cause a paradox, its probability goes to zero. Effectively, you can't perform that action successfully. Instead, the universe biases outcomes toward consistency. This is sometimes called a post selection model. In the assassin grandfather scenario, your gun misfires at the crucial moment due to a 1 in a million malfunction. Something always happens to prevent the inconsistent outcome. You might call it fate or physics, but either way, paradoxical events have zero probability. Self consistency is a comforting resolution because it means you can time travel, but you can't mess things up. It also implies a kind of determinism or predestination. The timeline is fixed, and you, the time traveler, were always part of it. This is a common theme in fiction as well, where attempts to change the past end up causing the very events one tried to prevent. Think of the Greek myth of Oedipus, or more modern stories where prophecies are fulfilled by the hero's attempts to avoid them. Finally, chronology protection, which we've touched on via Hawking. This is less a resolution within a story and more a conjecture about physical law that nature simply doesn't allow time machines to function. So maybe wormholes collapse, cylinders require impossible matter, cosmic strings of needed mass don't exist, etc., in any scenario that would allow a paradox. Hawking half jokingly said, "This keeps the world safe for historians." If chronology protection is true, we'll never face a grandfather paradox because we'll never actually get a time machine off the ground in the first place. This could manifest as engineering problems. Some effect always prevents completion, or even if built, something weird stops it from creating a closed time-like curve, like a burst of energy or the formation of a horizon, etc. In the Scientific American piece, Kip Thorne concluded any time machine is likely to self destruct at the moment of activation, which is a dramatic way of saying chronology protection might kick in. Which of these is correct? We don't know. Many physicists lean toward chronology protection for the simple reason that it avoids the sticky paradox issue entirely, and they see no evidence of time travelers among us. Others keep open minds. Perhaps the universe allows time travel, but in a way we don't yet fully grasp, like many worlds or consistency. In a multiverse scenario, time travel might be rebranded as universe hopping, with each jump landing you in a different branch's time. In a consistent universe scenario, time travel could be possible but constrained. You can fulfill the past, not rewrite it. There's also a more existential consideration. If time travel were commonplace in the future, wouldn't we know? The absence of obvious visitors from the future, unless they're very good at hiding, might imply something. Hawking once hosted a party for time travelers, sending out invites after it happened, and no one showed up, which he took as evidence against time travel at macroscopic scales. Of course, that's a playful experiment, not definitive proof of anything, but it illustrates the point. As you relax into this discussion, consider how each of these solutions feels. The parallel universe, one suggests a vast foam of realities, where every choice or time travel creates new branches. The self consistency one suggests a perhaps tighter constraint, a single reality that cannot be broken, only bent into loops. Chronology protection suggests our hopes of time hopping will always be frustrated by nature's caution. There's even the possibility that time travel occurs, but we live in a kind of protected timeline that future time travelers aren't interested in or able to access. Some have whimsically suggested maybe the past is just too boring, or time travel is heavily regulated in the future, such that no rogue tourists come popping up. Who knows? It's worth noting that quantum physics introduces its own twist on these ideas. Some interpretations of quantum mechanics, like the many worlds interpretation, blend well with the parallel timeline idea. Others have tried to design quantum experiments to test self consistency on small scales, for example, simulating a particle interacting with its past self. In fact, let's explore that briefly in the next section, how the quantum world hints at or simulates time loops and what that tells us. After all, time travel theories that could actually happen might not be limited to big cosmic objects. Perhaps at the quantum level, time loops and subtle, backward in time influences could be real. We will look at some quantum experiments and ideas that play with time, and then gently come to a conclusion about what all this means for us dreaming about time travel in the wee hours. Quantum time loops, subatomic trips, and trickery. Down at the smallest scales of reality, the rules of quantum mechanics reign, and they are famously strange. Particles can exist in multiple states at once. Events can be entangled across distance, and the act of observation itself can alter outcomes. It turns out, quantum theory also allows us to toy with time in intriguing ways, at least in thought experiments and simulations. While we don't have a quantum time machine that sends people to the past, physicists have used quantum computers to simulate time travel paradoxes, and some interpretations of quantum physics suggest that subtle forms of retrocausality, effects preceding their causes, might be possible without contradiction. Could it be that time travel, if not feasible for humans, might still occur in the subatomic realm? One idea proposed by physicist David Deutsch in the 1990s was to consider a quantum particle interacting with its past self via a closed time-like curve. Deutsch formulated a consistency condition that effectively merges the many worlds interpretation with time loops, ensuring no paradox happens. In his model, a qubit, quantum bit, that goes back in time to collide with itself might emerge in a state that is a fixed point of the interaction. Subsequent research has expanded on this, for instance by using photons in optical experiments to mimic a qubit going back in time. The results tend to support the idea that quantum consistency can be maintained, often at the expense of predictability in individual cases, but overall no paradox. In 2020, a team of researchers used a quantum computer, the IBM Quantum Cloud, to simulate the grandfather paradox in a quantum context. They essentially programmed the logic of a time travel scenario, the quantum equivalent of a person going back and potentially killing their grandfather, and observed what happened according to quantum rules. They found that the paradox could be resolved. When a quantum particle goes back in time, in the simulation, It cannot but perform an operation that contradicts its own past state. In quantum terms, certain histories interfere and cancel out, leaving only self consistent ones. Their conclusion was that quantum mechanics, with its probabilistic nature, smooths out the paradox. In a way, the universe allows time travel as long as it's within the fuzzy, uncertain bounds of quantum states where multiple possibilities exist and the only consistent histories survive. If that's how the real universe operates, it might mean that a macroscopic paradox with definite outcomes like alive or dead grandparents would never come to pass because the fundamental level is quantum and would avert it. Another famous quantum thought experiment is the delayed choice quantum eraser, which at first glance looks like affecting the past. In that experiment, the decision to observe a particle or not, which can be made after the particle has entered an apparatus, seems to retroactively determine whether it behaved like a wave earlier. However, it doesn't allow signaling to the past or true contradiction. When examined carefully, the message can't be extracted in a way that breaks causality. What it does show is that the separation between past and present can be very subtle in quantum mechanics. The outcome only becomes concrete once all pieces come together. Some physicists interpret such experiments as evidence that time as we perceive it may not be fundamental. Past and future might be tied together in one quantum state until measured. There's also a concept called quantum retrocausality, where some interpretations, like the two state vector formalism or certain hidden variable theories, suggest that events in the future could influence the past on a quantum level without enabling full fledged time travel. These are speculative and not widely accepted, but they underscore that quantum theory leaves room for time to be less straightforward than our classical experience suggests. While all this is quite esoteric, it has a reassuring angle for our discussion. It hints that the universe might be built in a way that accommodates time loops without logical disaster, at least microscopically. If one day we figure out how to unify quantum physics with gravity, quantum gravity theory, maybe we'll find that closed time-like curves are not forbidden, just very tricky to utilize in a controlled way. Quantum computations that include CTCs have shown, for example, that one could potentially solve certain problems much faster because you have a kind of strange computational power when you can query yourself from the future. But thankfully or not, it also shows that our usual understanding of information might break down in those scenarios as cause and effect blur. For a gentle mental picture, envision a single photon of light that, through some clever optical setup, appears to meet an echo of itself from earlier. The two interfere, sometimes canceling each other out, sometimes reinforcing, and only certain outcomes survive this self interaction. It's as if nature allows the photon to traverse a little loop in time, but ensures that it comes out the other end in a state that doesn't rock the boat of overall consistency. If an inconsistency threatened, like one path says, I exist, and the other says, I don't, those paths interfere destructively and vanish. The photon always ends up taking a path that is consistent with itself. Now scale that up in your imagination. If a person were in a time loop, maybe all their choices and chances would whittle down such that only a consistent set of actions is possible, It might feel like free will is constrained by fate in those loops, or that coincidences abound to stop paradoxes. This aligns quite nicely with the Novikov principle we discussed, just seen through a quantum lens. It could very well be that if time travel is ever achieved by advanced beings, they will find that they cannot change history. They become part of it. Or, if multiple histories can happen, they branch off and don't interfere with each other. As you listen to these ideas, perhaps in a semi drowsy state, it's almost like hearing about the secret rules of a grand game. Time, that steady river, has eddies and whirlpools that we suspected might exist. If you try to paddle against the current, travel to the past, the water might simply carry you in a loop and deposit you back without altering the main flow or split you into a separate stream. Ultimately, whether through quantum subtlety or cosmic censorship, the universe seems to have ways to prevent the absurd. We have journeyed through many theoretical landscapes: extreme gravity, near light speeds, wormholes, cosmic strings, gigantic cylinders, tachyons, rotating black holes, and quantum loops. Each offered a glimpse of how time travel could happen, but each came with challenges or safeguards. Let's now step back and conclude our long exploration. In the concluding thoughts, we'll try to synthesize what we've learned and reflect on what time travel theories tell us about the nature of reality, and perhaps why simply enjoying the present moment or drifting off to sleep might be just as well, given the convoluted and possibly perilous paths required to wander through time. Time dilation and GPS, clocks out of sync across the sky. We begin our gentle journey through time with something that might surprise you. Time travel is happening around us right now in subtle ways. If you close your eyes, you can almost feel the steady ticking of a clock. Imagine two clocks ticking in unison, one beside you on Earth and another high above on a satellite quietly orbiting the planet. These two clocks will not stay in perfect sync. In fact, ever so slightly, the one in space drifts ahead in time. This is not science fiction, it's a real effect of Einstein's theories of relativity known as time dilation. The faster an object moves, or the farther it is from a source of gravity, the more time stretches and slackens for it compared to an observer on the ground. Picture yourself standing under a vast night sky, stars wheeling slowly overhead. Above, a GPS satellite hurtles around Earth at 14,000 kilometers per hour, carrying an ultra-precise atomic clock. Down on Earth, a twin clock sits at rest. To your intuition, time flows the same for both. A second is a second, a minute is a minute. But according to relativity, the moving clock high above ticks a touch slower due to its speed, and at the same time ticks a touch faster due to feeling weaker gravity than the clock at Earth's surface. The differences are minuscule, mere millionths of a second, yet they accumulate. Each day, the satellite's clock gets about 38 microseconds ahead of the Earth clock when both effects are combined. 38 microseconds, 38 millionths of a second, might seem laughably small, but even such a tiny lead would muddle your GPS location by kilometers if left uncorrected. Fortunately, the engineers who built the GPS system knew about this relativistic quirk. They implemented adjustments so that the satellite clock's tick slightly slower from the start, canceling out the relativistic gain. As a result, GPS satellites have effectively become an ongoing experiment in time travel, continuously proving Einstein right as they extend a fraction of a second into the future each day and then resynchronize with Earth. Every time you use your phone or car navigation, you're quietly benefiting from time dilation, a real, modern kind of time travel happening above you in the calm darkness of space. To grasp this deeply, imagine a pair of twins born at the same moment. One twin remains on Earth, living an ordinary life. The other twin boards a spaceship and travels fast, incredibly fast, near the speed of light, on a journey among the stars. When the traveling twin finally returns home, something astonishing has happened. The traveling twin is younger than the twin who stayed on Earth, perhaps only by a few years or even just weeks, depending on the trip, but undeniably younger. This is the famous twin paradox, which is not a paradox at all, but a real prediction of relativity. Motion slows the passage of time for the traveler. In our story, the spacefaring twin literally leaps forward relative to the stay at home twin, having aged less. If you were that traveler, you would step off your spaceship into your own future, a future where your sibling has grown older without you. Although jetting off at near light speed isn't feasible for humans yet, time dilation is well demonstrated with airplanes and satellites. In one early experiment, scientists flew atomic clocks on commercial jets around the world. When compared to clocks on the ground, the airborne clocks had fallen out of sync. They were just a little behind, having experienced a slower flow of time during flight. And as we've seen, satellites orbiting Earth must account for both special relativity, motion, and general relativity, gravity's effect on time, to keep our measurements accurate. These real world tests confirm something profound. Time is not absolute. It can stretch and shrink gently, depending on speed and gravity, allowing nature to slip someone or something a little way into the future. Let's pause and absorb the calm wonder of that. High above you, clocks tick to a slightly different rhythm. The flow of time itself is flexible, stretching like taffy under the right conditions. No fantastical machines or magic portals are needed, just speed and altitude. Einstein's universe blends space and time together so that a fast moving or high flying traveler experiences less time, effectively finding themselves arriving in a future not shared by those left behind. Next time you gaze up at a passing airplane or a satellite glinting in the sun, consider that its passengers or onboard clocks are time travelers of a sort, riding the gentle currents of space-time to arrive home ever so slightly younger or later than they otherwise would. The difference may be microscopic, but it is real, the first step on our journey through plausible time travel. It shows that nature permits, even demands, these deviations in elapsed time. From this foundation, we can dream of more dramatic possibilities. After all, if speed can twist time, what other strange phenomena might let us venture further, perhaps even backward? The road ahead, winding through science and speculation, will remain soft and fascinating. We will drift onward, ever so calmly, deeper into time's mysteries, guided by both imagination and the gentle light of scientific knowledge. Before we move on, take a slow breath. Above us, the satellites continue to glide, their clocks ticking to a slightly different beat. Time travel has already begun, quietly, all around us, in the bending of time's pace. With that reassuring thought, let's gently step forward to the next idea, one that pushes our musings to the very brink of what nature might allow. We've seen time slow and quicken. Now we ask, could time perhaps reverse or loop in unexpected ways? In the next chapter, we'll explore a theoretical possibility that tests the limits of physics, particles that outrun light itself, and what that means for cause and effect. Tachyons and faster than light travel, chasing shadows of tomorrow. In the soft twilight of our exploration, we now turn to a truly speculative path. What if something could travel faster than light? Imagine for a moment that you are outside on a warm evening, watching a thunderstorm flicker on the horizon. You see the distant lightning before you hear the thunder because light outruns sound. Now, stretch your imagination further. What if something could outrun light? What would it look like if a beam of light itself were left trailing in the wake of a mysterious, superluminal entity? Physics, as we know it, strongly suggests that nothing with mass can accelerate to or beyond the speed of light. Einstein's special relativity set this cosmic speed limit, showing that an object's mass would grow and time would slow to a stop at light speed, making it impossible to push further. Yet, theoretical physicists have asked, is there a loophole? Could there exist particles that always move faster than light, never slowing below that threshold? Such hypothetical particles have been given a whimsical name, tachyons. Tachyon comes from the Greek word for swift. By definition, a tachyon would break the light speed barrier as casually as a sound wave breaks the sound barrier. It would be a traveler from beyond our visible horizon, always racing ahead. If tachyons exist, and it's a big if, they would come with astonishing properties. According to relativity, as a tachyon loses energy, it would speed up, the opposite of what we're used to. At infinite speed, it would have zero energy, and to slow down to light speed, it would need infinite energy. This strange inversion hints at something even more startling. From our perspective, a tachyon might appear to move backward in time. Faster than light travel and backwards time travel are two sides of the same coin in relativity's equations. If a particle goes superluminal, there will be some viewpoint from which the effect of its journey is seen before its cause. In simpler terms, a tachyon leaving point A and arriving at point B could, to some observer, reach B before it left A. This is a slippery concept, so let's create a gentle mental picture. Envision a peaceful lake at dusk. Two fireflies represent events in time. Firefly A twinkles, then Firefly B twinkles. Normally, everyone agrees A came first, then B because information, like light, from A reaches B no faster than light allows. Now imagine a fanciful scenario, a superluminal signal, a tachyon flash, linking A to B. To you standing on one side of the lake, maybe A's glow still seems to precede B's. But someone on the opposite shore, moving in a different way relative to the fireflies, might swear B happened first, and a second. Both perspectives are valid in relativity. With a tachyon in play, cause and effect become relative, tangled up with how one is moving. In one observer's experience, the effect could genuinely occur before its cause. This opens the door to unsettling paradoxes. Let's say you possess a tachyon transmitter, a fanciful device to send messages faster than light. You decide to send a brief message to a friend far away, a simple hello from the future. Thanks to the tachyon's quirks, your friend might receive that message before you even press send on your device. Suppose in confusion, your friend then tachyon transmits back, "Don't send me any message." In a bizarre twist, you receive their reply before you sent the initial hello, causing you to decide not to send anything after all. But if you never sent the first message, how did your friend reply to it? We have entered the realm of the grandfather paradox, a causal loop with no beginning, an effect preventing its own cause. In our calm and logical bedtime journey, this sounds like a riddle whispered in the dark. Nature, as far as we understand, abhors such contradictions. One resolution could simply be that tachyons don't exist. They remain an elegant idea that reality forbids. Another possibility is that tachyons exist but are forever isolated from normal matter, unable to interact or convey information in any useful way. They might flicker in and out of existence beyond our grasp, causing no paradoxes because we can never control them. In that case, tachyons would be like shadows of tomorrow, always present in theory, but never allowing us to catch them or harness them to change today. Physicists have also imagined creative escapes from the paradoxes. Perhaps any attempt to use a tachyon for mischief triggers some unknown principle that preserves consistency. Some suggest the universe might enforce a rule. You can send a tachyon, but you can't send information. The tachyon's signals might become jumbled or meaningless, ensuring no causality is violated. In that scenario, tachyons could flit about without wreaking havoc on the timeline. All of these musings remain speculative. Over the decades, scientists have looked for any sign of tachyons in cosmic ray showers, in particle accelerators, but none have been confirmed. The silence of experimental evidence makes tachyons a ghost in the equations, a maybe myth. Yet, they serve a beautiful purpose in our exploration. Tachyons teach us how closely time and light are woven together. They remind us that if we dare to slip faster than light, even in thought, we begin to slip backward in time. In our minds, we can imagine surfing a wave of tachyons, gliding so fast that the stars around us rewind and the universe plays in reverse. For a moment, imagine yourself as a tachyon. You have always existed in a strange state of faster than light motion. You see events in a mixed up order that others would find impossible. Perhaps a glass shatters, and you see the fragments leap back up to reform the whole simply because, from your viewpoint, the shards scattered slower than you raced past them. The normal sequence of cause then effect is blurred. It's a disorienting but oddly serene vision, as if you wander through a dream where time is just another direction you can turn toward or away from. Now, as we continue our meditative expedition, take comfort in this. Even though tachyons might not be real, Pondering them reveals how deeply rooted causality is in our world. Every comfortingly consistent day we live, where causes precede effects, is upheld by the cosmic speed limit. Light's finite pace is like a guardian of order. Should we overturn it, even in a thought experiment, we find ourselves entangled in paradox. The universe kindly keeps our everyday cause and effect safe by disallowing such tangled timelines, at least as far as we have observed. We have gently tested the limits of speed and seen the intimations of backward time travel they bring. But there are other ways the past and future might mingle. Not all involve rockets or hypothetical particles. Some ideas suggest that the future and past could touch each other through subtle quantum phenomena or other exotic mechanisms without anything as dramatic as a tachyon. These concepts fall under the dreamy notion of retrocausality, effects preceding causes in surprising ways. Let's drift onward to explore that, keeping our thoughts as light as the night breeze. We leave behind the tachyon's hypothetical wake and step into the delicate world of quantum possibilities and reversed causation, all in a calm and open frame of mind. Retrocausality, when tomorrow reaches back to yesterday. Let's gently step into a world where the arrow of cause and effect softens and curls back on itself. The concept we're entering is called retrocausality, which means backwards causation, an effect happening before its cause, as strange as that sounds. In the stillness of our thoughts, imagine a pond at dawn. You toss a pebble in, and ripples spread out. Normally, the pebble's splash causes the ripples, but picture retrocausality. You see ripples converging inward before you drop the pebble, as if the pond somehow knows the stone is about to fall. Only after those pre-ripples meet does the pebble plop in exactly where the ripples had gathered. It's as though the future event, the pebble's fall, cast a shadow rippling backward in time. In everyday life, we never see this. Causes lead and effects follow with comforting consistency. However, in the subtler language of physics, especially quantum physics, the distinction between past and future can become blurred. At the deepest level, the equations that govern particles don't insist on a direction for time. They often work equally well if you imagine time running backwards. Particles care about energy and momentum and the dance of forces, but not so obviously about what we call past or future. Some physicists have proposed that certain quantum phenomena could be interpreted as the future influencing the past. It's a delicate and controversial interpretation, but a fascinating one for our sleepy exploration. One famous example to ponder is known as the delayed choice experiment, a mind-bending quantum thought experiment, and later, actual experiment. We won't dive too deeply into technical details, but the essence is this. A particle like a photon can behave like a wave taking two paths at once. If you wait until after it has passed a fork to decide whether to detect it, thus forcing it to choose a path, the photon appears to have already chosen appropriately, even if that decision happens well after it should have gone through the fork. In other words, how you observe it now seems to affect how it traveled earlier. To some, this suggests the photon's future measurement reached back and altered its past behavior, a hint of retrocausality in the quantum realm. While there are other interpretations, and no information can be sent to truly change the past in these experiments, it leaves us with the eerie feeling that time at the microscopic level is far more fluid than our intuition suggests. Another gentle image. Think of two entangled particles born together and flying apart. They share a mysterious bond. If you gently measure one, the other seems to know instantly and adjusts its state, no matter how far away it is. Traditionally, we say this correlation just is. Neither cause precedes the other, as if they were two notes of a chord struck simultaneously. But a retrocausal view would say perhaps the measurement of the first particle sends a subtle influence backward in time to the moment of their creation, which then flows forward to determine the second particle's state. This way, no signal travels faster than light through space. Instead, a kind of influence loops through time. It's a bit like if twins separated at birth. Both decide to wink at the same moment, not by telepathy, but because one twin's future decision to wink travels back to their shared past and then forward to the other twin. A strange idea, indeed. Physicists such as John Wheeler and others have mused on such possibilities. Wheeler even imagined that perhaps every electron in the universe could be the same electron zigzagging through time, reappearing over and over, an extreme retrocausal vision in which one particle's world line coils through the ages, meeting itself countless times. While that specific notion isn't taken literally, it poetically captures how quantum physics sometimes blurs identity and time. The equations of Richard Feynman treat positrons, anti-electrons, as electrons moving backward in time. It's a mathematical trick that works beautifully. Instead of thinking an antiparticle popped into existence and annihilated an electron, you can equivalently think the electron briefly went back in time and erased itself. Don't worry if this is hard to digest. It's mind-bending even to experts. The key takeaway is that the fundamental laws seem to allow time flips and loops on paper, even if in reality we mostly observe a neat order of causes and effects. Let's bring this back to a calm, experiential place. Have you ever had a moment when you felt like you knew something was about to happen, and then it did? Perhaps thinking of an old friend just before they call, or feeling an inexplicable sense of deja vu when an event unfolds. Usually, we chalk these up to coincidence or subtle, unconscious clues. But retrocausality invites us, in a very gentle way, to wonder, could the future sometimes cast an echo into the present? Not in any grand, change your life way. If it happens at all, it would be fleeting, delicate, like a single snowflake falling backwards up to the cloud. We should remain grounded. Mainstream science doesn't endorse the idea that you can send clear signals to the past. Retrocausality is largely a theoretical exploration, a possible interpretation of quantum puzzles. Yet simply considering it can be strangely comforting. It suggests a universe where time is perhaps not a one-way street, where the tapestry of reality is woven with threads that loop in curious patterns. If true, it might mean that every moment is an intricate mix of influences from both past and future, all self-consistently arranged so that no paradox rips the fabric. One researcher, for example, Dr. John Kramer, explored whether quantum entanglement could be used to communicate backwards in time by clever setups. He found that all such schemes failed. Something always prevented actual information from traveling against time's grain. Still, the effort itself is telling. Brilliant minds are testing the edges of causality, like someone gently pressing on a membrane to see if it gives. So far, the membrane of time holds firm for transmitting messages in reverse, but our musings can slip through that membrane like a phantom. Think of retrocausality as a soft whisper in physics. It doesn't shout or overturn your world, it merely hints. Perhaps the story of cause and effect is richer than you know. Perhaps the universe has a subtle ability to heal contradictions by arranging events in just the right loop. If you were destined to go back and save your past self, retrocausality might say you had already been saved by that future you in a self consistent way, and you just didn't realize it was you who did it from the future. It tickles the imagination gently, the idea that the boundary between past and future might be porous in places, with tiny eddies where time swirls rather than flows straight. As we continue, resting in this cozy bubble of thought, remember that retrocausality hasn't given us time machines or clear answers. It remains a speculative lullaby, a way to question the rigidity of time. We remain safely in our present, our causes followed by effects as normal. But having allowed ourselves this dreamy detour where tomorrow might reach into yesterday, we're better prepared to appreciate why, in the macroscopic world, time feels so strictly one way. The next chapters will explore why time's arrow points forward so relentlessly, and how that arrow might be tied to something as humble and all pervasive as heat and disorder. So let's drift further, guided by the question: if physics sometimes permits time loops, what in nature makes them so rare or hidden? We will find our answers in the concept of entropy as we continue this gentle voyage through time's mysteries. Thermodynamic time asymmetry, the one way street of entropy. Every day, without even thinking about it, we witness countless tiny acts of time travel, but they all go one direction. A teapot cools down on the counter, never spontaneously heating up. Cream disperses in coffee, never separating back out on its own. We remember yesterday, but we do not remember tomorrow. This common sense flow from past to future, from ordered to disordered, is captured by a principle in physics, the second law of thermodynamics, which introduces us to the concept of entropy. In a poetic sense, entropy is the universe's built in arrow of time. It's a measure of disorder, and it tends to increase as time marches on. This creates a fundamental asymmetry in time. While the basic laws of physics are mostly time symmetric, they don't care which way the clock runs. The overall behavior of large collections of things has a preferred direction toward greater entropy. Let's unpack that gently. Thermodynamic time asymmetry is a fancy term for the simple observation that many natural processes are irreversible. If you crack an egg and scramble it, you can't unscramble it. The molecules dance into a new, more disordered arrangement, higher entropy, and it would be astronomically unlikely for them to all dance back to the neat order of an uncracked egg. Technically, nothing in the microscopic laws forbids the reverse. It's just so improbable that it will practically never happen. This gives time a direction. Forward is the direction of increasing entropy. As one moves forward in time, entropy in an isolated system can increase but not decrease. It's as if the universe has a giant clock built into it, not made of gears or electronics, but of the collective tendency of all things to move from order to chaos. Imagine a pristine sandcastle on the beach. As the days go by, wind and waves gradually erode its sharp towers and walls. Eventually, it becomes just a formless mound of sand, higher entropy than the organized castle. You'll never see the wind spontaneously carve the mound back into a perfect castle. It's not forbidden by Newton's laws of motion. It's just exceedingly, absurdly unlikely. This unidirectional crumbling of order is the thermodynamic arrow of time in action. In a more everyday image, think of how your tidy room tends to get messier if left alone, but a messy room never tidies itself without effort. Disorder grows. Order requires work to maintain. The forward flow of time is intimately connected to this growth of entropy. But what exactly is entropy? In simple terms, it counts how many ways the ingredients of a system can be arranged without changing its overall appearance. A cup of coffee with cream swirled in has high entropy because the molecules can be jumbled in many microstates and it all looks uniformly mixed. In contrast, a cup of coffee with a separate layer of cream on top has low entropy, a very special, orderly state that could be rearranged in myriad random ways, stirring it up, to yield the mixed state. Entropy is higher in the mixed state because there are more possible configurations of molecules that look mixed than configurations that look neatly separated. So, as the coffee and cream mix, they're moving from a less probable low entropy arrangement to a more probable high entropy one, statistically speaking. Time's asymmetry emerges from this march toward the statistically likely, the many possibilities state, rather than the few possibilities state. Now, take a slow breath and consider an amazing fact. Aside from this thermodynamic law, almost all fundamental physical laws are time symmetric. If you could watch a microscopic interaction, say two particles scattering off each other, and run the movie backwards, it would usually look perfectly plausible, as if it could have happened normally. At the level of fundamental forces, there's rarely a built-in arrow. A video of orbiting planets or colliding billiard balls doesn't obviously tell you if it's being played forwards or backwards. Only when you have many particles together, like in a gas or a pot of soup cooling down, does an obvious direction appear. The messy direction, the direction of heat spreading out, of differences evening out. Entropy is what allows us to intuitively guess the flow of time in a video. For example, if you see a video of smoke gathering itself into a cigarette, you instantly suspect the video is reversed, because that would represent entropy decreasing, which doesn't happen naturally. This asymmetry in time might at first seem at odds with our previous chapter's whimsical ideas of retrocausality. How could the future influence the past if entropy is always climbing toward the future? One way to reconcile them is to realize they operate on different levels. Retrocausality and time symmetry can exist in the fine print of quantum equations or in narrow circumstances without upsetting the grand thermodynamic march. The second law acts like a grand enforcer, ensuring that, overall, chaos increases and thus straightforward, backwards in time influences remain hidden or microscopic. The source of the thermodynamic asymmetry is still somewhat mysterious. The equations of physics themselves don't force entropy to increase, they allow for it, but they'd equally allow it to decrease. So, why in our universe did we start in an extremely ordered state, low entropy, such that there was room to increase? This touches on deep cosmological questions. Many physicists think the very beginning of the universe, the Big Bang, must have been a state of remarkably low entropy, an almost impossibly orderly arrangement of energy and matter. As the universe evolved, there was essentially nowhere to go but toward higher entropy, like a wound up clock spring unwinding over billions of years. The arrow of time may ultimately stem from cosmic initial conditions. The universe began in a special, highly ordered state, and ever since, entropy has been increasing. We are all riding that gradual slide from order toward disorder, even stars shining and people thinking are part of that entropy increase. We and everything around us generate entropy as we live. Whenever you burn calories, or your cell phone battery discharges, or a star fuses hydrogen, entropy produced in the process wafts out into the environment. The total entropy of the universe goes up irreversibly with every breath you take, which warms the air and spreads out energy. And every thought you have, yes, even brain activity produces a tiny bit of heat. Entropy is sometimes poetically called time's arrow because it gives a universal way to distinguish past from future. Past times had lower entropy, future times have higher entropy. Now, what does this mean for time travel? A time machine that sends you to the past, if such a thing were possible, would have to contend with the entropy difference. You'd be injecting a high entropy being, full of the disorder accumulated through your lifetime, into a lower entropy era. How would that entropy be accounted for? One might speculate about exotic phenomena that could locally reverse entropy, but as of now, none are known outside of clever tricks that only work in very restricted systems and never violate the second law for the whole closed system. The second law is extremely robust. It's never been observed to falter. It's as if nature has a rule that says, you can't clean up this chaos without paying the price elsewhere. You can locally decrease entropy, like when a refrigerator cools the food inside, but at the cost of increasing entropy by a greater amount somewhere else. The fridge's motor generates heat into the room. Globally, the disorder still rises. Thermodynamic time asymmetry, therefore, might be seen as time's built in safety net against paradoxes. It ensures that broken eggs don't leap off the floor and reassemble, that we can't remember forward, and that any subtle retrocausal quantum effects average out so innocuously that they never violate the common sense order of life. It provides a direction, a gentle but inexorable push from what we call past to what we call future. While Einstein's spacetime and the equations of motion are symmetric, entropy adds the arrow that defines a before and after. As you lie here contemplating, perhaps you sense the room around you cooling slightly as night deepens, or your body relaxing and releasing heat. That's entropy increasing in small ways, a sign that time is passing in the usual direction. It's a comforting, natural progression. Thermodynamic asymmetry assures us that time keeps moving forward on the macro scale, carrying us all from moment to moment. In the next chapter, we will delve a bit more into the idea of time's arrow and entropy's role, reflecting on how this arrow intertwines with memory, perception, and the possibility of reversing time. We'll see that the arrow of time is not just a physical concept, but something that underpins our very experience of life. So let's continue, ever so gently, to explore why time only seems to flow one way for us, and what that means for any would be time traveler. The role of entropy and time's arrow, memory, perception, and the irreversible now. Feel the quiet of this moment. You can likely remember what you had for breakfast this morning, but you have no knowledge of the breakfasts you will have in 10 years. This simple truth, that we remember the past and not the future, is deeply tied to time's arrow and entropy. In our last chapter, we explored how entropy's one-way increase distinguishes past from future in the physical world. Now, let's consider how that one-way street of time plays out in our minds and in the fabric of reality, and why it might be essential for keeping the universe sensible and hospitable to us conscious beings. Every memory you form, say remembering a calm walk you took yesterday, is essentially the encoding of some information in your brain, a pattern carved into your neurons. Creating that memory increased entropy in your brain and body. Chemical energy was expended, heat released. But to recall it now, you retrieve the stored information and experience a recollection. We can only store records of the past because entropy was lower back then. It's like writing in wet cement that later hardens. By the time you get to the future, the cement of those events is set. You have them as records. The future, by contrast, hasn't happened, so there are no records of it yet. This asymmetric recording of information is one way the arrow of time manifests. Another way to look at it is that every cause leaves multiple imprints or effects, higher entropy, which then leave more imprints, fanning out like branches of a tree into the future. But effects rarely converge neatly to erase themselves and reconstruct a singular cause. That would be going against an increasing entropy. For example, the presence of a lit candle in a room causes many effects. Light reflects off surfaces. A bit of soot might deposit on the ceiling. Warmth spreads. Molecules of wax disperse their scent. Later, from those traces, one could deduce a candle had been there, perhaps the scent lingering or a tiny smoke stain. The past event left footprints in the present. But imagine trying to place a candle in the room in the future by somehow spontaneously assembling all those traces first. Absurdly difficult because it demands a highly coordinated decrease in entropy. Thus, past events are etched into the present, whereas future events are a blank slate waiting to be written. Time's arrow is essentially the direction in which information and influences accumulate, not disperse. Zooming out to the universe's grand scale, we're all voyaging from a highly ordered cosmos, the hot, uniform, early universe, to an increasingly disordered one, stars burning out, matter spreading thin. The arrow of time is aligned with the growth of disorder. It's intriguing that if you hypothetically lived in a universe where entropy decreased with what you call forward time, everything we consider normal would flip. You might remember the future and not the past. You might see tea unmixing and smoke gathering into logs, but your brain too would operate in reverse fashion. Oddly, you might not find it strange. To you, that would be normal, and the reverse sequence would feel forward. It's a bit of a logical twist. If time reversed and entropy decreased, but you were part of that reversal, you likely wouldn't notice anything amiss because your perceptions would run backward correspondingly. Philosophers often pose this thought experiment. If the entire universe and everyone's memory ran backward, would we be able to tell? Probably not. We'd still experience things as moving from past to future according to how we're built. So time's arrow, enforced by entropy, is also what makes our experiences coherent and unified. It ensures we don't get causality scrambled at macroscopic scales. Arrows hit targets after they're shot, never before. We drop a glass and then it shatters, never the reverse. Because of this reliability, we can make sense of the world. We can infer causes from effects, like detective work, because the effects fan out from causes. If cause and effect were symmetric and loops were common, imagine how confusing everyday life would be. A glass might spontaneously reassemble on the table because somewhere in the future someone will knock it off. Thankfully, entropy's arrow protects us from such chaos, anchoring effects firmly after their causes. In terms of time travel implications, the arrow of time means that even if you somehow went back, you'd be swimming against a mighty current of increasing entropy. Some authors and thinkers suggest that a time traveler to the past would face a world that is fundamentally wrong for them thermodynamically. Perhaps memory would have to work strangely, or the environment itself might be hostile as you carry high entropy into a low entropy era. These are imaginative extrapolations, of course, but they highlight that time's one way arrow is a big hurdle for backward time travel. It's not just about building a machine, it's about the basic fact that the universe doesn't reset. It keeps moving towards equilibrium. For a calming analogy, think of time as a gently flowing river. All things are carried from upstream, the past, to downstream, the future. Entropy is like the slight downward slope that ensures the river has a direction to flow. Without that slope, the river might become a still lake, or worse, flow chaotically in all directions. But with the slope, there's a clear downstream. In our lives, downstream is where entropy is higher, tomorrow's entropy slightly more than today's. And just as you can't have a waterfall flow upward without external intervention, you can't have entropy spontaneously decrease. It's nature's watermark indicating which way is forward in time. However, it's worth noting a subtle point. While entropy tends to increase, it doesn't forbid local decreases. If you look at a small system for a short time, random fluctuations can momentarily decrease entropy. In principle, it's possible a very tiny amount of air in a room could spontaneously gather into one corner for a second, making that corner lower entropy. But for anything beyond a few molecules, the probability is so low that the age of the universe isn't long enough for it to happen even once. So practically, entropy only goes one way for large, noticeable things. In the quantum realm or micro realm, time symmetry still largely reigns, and fluctuations can occur, but they average out so that on the whole, the second law holds firmly. This tells us that time's arrow is a statistical truth rather than an absolute. It arises because the odds so overwhelmingly favor one direction. This statistical nature of the arrow gives a tiny glimmer of scientific speculation. Could some advanced technology manipulate probabilities or initial conditions to locally reduce entropy and simulate a bit of reverse time? Some have dreamt of Maxwell's demon, a thought experiment where a tiny demon sorts fast and slow gas molecules to decrease entropy, seemingly reversing the second law. In the end, though, even the demon must produce entropy to do its work, preserving the law's validity. It seems there are no free lunches in entropy land. As you rest and listen, the world's myriad processes carry on increasing entropy. Wood decays, stars emit heat, our sun sends out rays that Earth dissipates as lower quality heat to space, and so on. It's a grand, slow settling. Does this make the future bleak? Not really on human timescales. It's simply the natural order of time. The increase of entropy provides opportunities for life and growth in the interim. For example, the sun's energy fueling life, which increases entropy overall but allows local pockets of order, like our bodies, to flourish temporarily. One day in the far, far future, things may run down to a dull uniformity, but that's eons away. Right now, time's arrow ensures there's a difference between yesterday, today, and tomorrow, and that's part of what makes life and memory possible. So we can be grateful for entropy in a sense. It is the reason a broken egg stays broken. Imagine the confusion if it didn't. The reason we can remember things and learn, the reason causes led to reliable effects. It gives the cosmos a consistent narrative flow. Time travel fantasies often focus on breaking that flow, but we must understand how strong it is. As we wrap up our reflection on time's arrow, let's carry forward an appreciation that this arrow is deeply woven into the fabric of reality and consciousness. In the coming chapters, we'll shift perspective. We have so far looked at the physics of time travel and time's direction. Now, in a gentle transition, we will move to more philosophical and human centered musings. We'll ponder different philosophies of time, whether past, present, and future are equally real or only the present truly exists. Then we'll explore the remarkable time machine we all possess, the human mind. Together, these will round out our understanding of time before we drift into some mythical tales and final wonders. For now, take comfort in the steady arrow of time that points from the known past to the unknown future, and let yourself float contentedly downstream, knowing that this is the natural and peaceful order of things. Eternalism versus presentism, block time and the spotlight of now. Imagine for a moment that time is like a vast, quiet landscape. In one view of this landscape, all moments in time exist simultaneously, spread out like a panorama. Past, present, and future are like different places on a map, all there, all real, even if you aren't in all those places at once. This philosophical view is called eternalism, often illustrated by the block universe theory in physics. It suggests that the universe is a four-dimensional block of space-time, with time being another dimension much like space. If you could take a God's eye view of the block, you would see every event that has ever happened or will happen laid out in their four-dimensional positions. Nothing comes into being or ceases to exist. It simply is somewhere in time. In this serene, frozen vista, what we call now is just a subjective viewpoint, like in traveler's spotlight, illuminating one section of the map while the rest remains in the dark. In stark contrast, another view, presentism, says that only the present moment is real. The past has slipped out of existence, existing only in records and memory, and the future is yet to exist at all. The flow of time in this view is like a single moving spotlight or a wave front that continually brings new moments into reality and sweeps old ones away into nothingness. Imagine walking in darkness with a lantern. You only see what is lit right now, the present. Behind you goes dark as the light moves on, the past vanishes, and in front of you is dark until you step forward. The future is not yet real. This is a more common sense, everyday view. We feel like only now exists, and time passes. Which of these views is correct? It's a deep philosophical question, and people have pondered it for centuries. Eternalism finds support in Einstein's relativity, which links space and time into space-time and suggests that different observers moving at different speeds will slice now differently. What you consider happening right now on a distant star might be someone else's past or future due to relative motion. If now is relative, perhaps all moments already exist out there in space-time. Einstein himself famously hinted at a block-time perspective when he wrote a consoling letter saying, in effect, for those of us who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. In an eternalist block universe, time travel might be thought of as just finding a different route through the map. Everything is there, so theoretically you could visit another time, like visiting a different country, if you could find the path or a wormhole vehicle, for example. Presentism, on the other hand, resonates with our immediate experience of time. We feel the flow. The past feels fixed and gone, the future open and not yet determined. It preserves an intuitive sense of free will. Since the future isn't real yet, perhaps we really can influence what it will be. Many who favor presentism point out that we experience reality as a unfolding story, not a static film reel. There's also a hybrid view called the growing block theory, where the past and present are real, but the future is not yet. The block of space-time is growing as time progresses, adding new slices. Present becomes past, but with the future still empty. This is a compromise that keeps a real past. The history exists in an objective sense, but still says the future isn't real until it happens. In our meditative journey, let's picture eternalism gently. Visualize the times of your life as pages in a book lying open before you. There you are as a child on one page. Here you are now on another, and on a further page, perhaps a future you relaxing in a garden many years hence. In the block universe, all these yous exist, each at their own page in time. You, the you of this moment, are simply reading the book sequentially, experiencing each page in turn as the present. You can't flip around, but that doesn't mean other pages aren't there. It's a comforting thought in a way. In eternalism, moments we cherish aren't gone. They are timelessly real in their coordinate of space-time. Your first kiss, a beloved relative who passed on, a golden day yet to come, all still out there, like scenes in a timeless film. We only experience one frame at a time, but the film is complete. One could even muse that if time travel were possible, it would mean accessing those already existing slices of space time, not creating anything anew. Now contrast that with presentism's gentle beauty. Only this slice exists, but it is ever renewing, ever refreshing. The past is a memory trace in our minds and in records. It's not an active reality anymore. The future is a realm of possibility. In presentism, time is truly like a river that is flowing. The past water has gone downstream and is no more. The future water upstream hasn't arrived. Only the water under your feet is real. This perspective gives time a kind of dynamic quality. The universe is like a stage where new scenes are actively coming into being as time moves. For those trying to avoid paradoxes, presentism is appealing. If the past no longer exists, you can't very well go visit it, eliminating the classic grandfather paradox by default. Time travel to the future in presentism is just waiting, and time travel to the past is impossible because there's no past there to travel to. Which view helps you fall asleep better at night? Perhaps the eternalist idea that your cherished moments still exist might be comforting, or perhaps the presentist notion that painful past times are truly gone can be a relief. Philosophically, there's no consensus. Physics leans toward eternalism because of relativity's implications, yet our consciousness insists on something like presentism with its vivid now. Some thinkers propose that time might be emergent, that the flow we feel is a kind of illusion or a secondary effect of a deeper, timeless reality, aligning with eternalism. Others propose that time is fundamental and flows in ways we don't yet understand, leaving room for presentism or a growing block scenario. Now, how does this tie into time travel theories? Under eternalism, time travel doesn't break reality because the destination time is just another location in space time. If I travel to 1920, those events and people exist in the block. I was always part of that block if I go there. In fact, eternalists would say if time travel is possible and you do it, then you already were in 1920 as a time traveler. We just hadn't gotten to that page yet in our reading. This can allow consistent solutions to paradoxes. You can't change the past because your visit to the past is already part of it. Perhaps you tried to warn someone of a disaster and failed, and that was always how history went. Your very attempt might even contribute to the outcome. This is the idea of consistency constraints in time travel, which align well with the block universe. The past, present, future are fixed in the block. You can participate but not alter the grand structure. Under presentism, however, time travel to the past is a conceptual headache. If only the present exists, going to the past means what exactly? Creating it anew? Or does the act of time travel mean that past becomes present somehow? It's very murky. Most presentists would lean toward the past is gone, you can't go there. They might accept one way travel to the future, like hibernation or relativistic time dilation, which essentially skip you ahead, that doesn't violate presentism since you just didn't experience intermediate moments, but those moments still came into existence in the world. But backward travel doesn't square with a universe where only now is real. In our gentle exploration, we need not choose a side dogmatically. We can instead feel the difference. Eternalism feels like a still, starry night sky. All the stars, moments, are out there at once, shining eternally even if we only see some now. Presentism feels like a single bright star moving across the sky, constantly renewing the night with its light while others fade behind it. Both are beautiful in their own way. Perhaps reality has aspects of both. Some theories like to say maybe the laws are eternalist, block like, but consciousness brings a presentist spotlight effect. We live through time as if it flows. Or maybe the flow of time is something fundamental we haven't fully incorporated into physics yet, like a cosmic clock ticking that we haven't found the mechanism for. As you relax, you might imagine time either as a solid crystal, block universe, or as an ever playing melody, flowing time. One gives comfort of permanence, the other the excitement of true change and creation. No matter which, the mystery of time remains, one of the grandest there is. In terms of sleep and calm, perhaps we can extract this solace. If the block universe is real, then everything is okay. The future is already out there, so in some sense it's secure, and the past is preserved. If presentism is real, then we are free each moment to shape what comes next, and the pains of the past no longer exist, except in memory. Either perspective can be soothing. They are two different lullabies about the nature of time. Now, with these big ideas floating gently in our minds, we will transition to something more intimate and immediate: the time travel abilities of our own mind and consciousness. Regardless of what time is out there, we humans have a remarkable gift. We can mentally revisit yesterday or imagine tomorrow in great detail. In the next chapter, we explore chronesthesia, the mind's time machine, and related puzzles like deja vu and consciousness loops. It will be a soft journey inward, complementing the cosmic and philosophical vistas we've just wandered through. Take a slow breath. Feel the present moment, the only moment we ever truly hold, and let's drift into the exploration of inner time travel. Chronesthesia, the mind's eye, travel through past and future. Without any machine at all, you possess the ability to time travel. Close your eyes and recall a warm memory from childhood, perhaps a sunny afternoon playing without a care. For a moment, you are there again. Now let your mind wander into the future. Envision yourself in a cozy home many years from now, watching a sunset. In that imagining, you visit a tomorrow that hasn't yet come. This remarkable mental ability is known as chronesthesia, a term psychologists use to describe the brain's ability to be aware of past, present, and future, and to mentally travel among them. It's sometimes simply called mental time travel. Chronesthesia is a gentle superpower of the human mind. Endel Tolving, a prominent memory researcher, coined this concept to highlight that humans, and perhaps some animals to a lesser degree, can do more than live in the present moment. We constantly wander in time mentally. We re experience past episodes, episodic memory, and pre experience possible future scenarios, imagination, and planning. Our consciousness has a kind of built in time machine that doesn't defy physics because it doesn't move our bodies, only our perspective and thoughts. Yet, how profound this is! I can be a child again in mind or preview my elder years, all while lying still in bed. This ability is what allows us to learn from the past and plan for the future. When you remember what you did yesterday, you're effectively time traveling to a real past event stored in your brain's archives. When you think, tomorrow I will go to the store, you mentally place yourself in tomorrow and run a little simulation. Our brain maintains a continuous awareness of past, present, and possible future, enabling us to navigate life beyond the immediate now. It's as if your consciousness is a little boat that can sail upstream into memory or downstream into anticipation. This is mostly a one-way trip in reality. We can't change the past we visit, nor do we know the future for sure. But the mental voyage itself is rich and useful. What's fascinating is how vivid these mental time travels can be. A daydream about the future can make you feel real emotions: excitement, anxiety, hope. A memory can trigger the warmth or sadness you felt in that original moment. The brain reactivates patterns similar to when we experienced the event the first time. In a calm, meditative state, you can use this to your advantage. Recalling positive memories or visualizing soothing future scenarios can bring real comfort in the present. For instance, if you feel stressed, you might close your eyes and recall a safe, happy moment, a beloved childhood home, a peaceful beach memory. By mentally traveling there, you often bring back a little of the peace from that time into the present. Similarly, imagining a pleasant future event, perhaps a coming vacation or seeing loved ones, can lift your current mood. This mental time travel is not perfect, of course. Our memories are sometimes faulty or incomplete, and our futures imagined can turn out differently. But even so, chronesthesia helps define our humanity. It's tied to our sense of self. You have a narrative of your life, what has happened and what might, and that continuity is because you can travel in your mind along your personal timeline at will. People who suffer certain memory loss or an inability to imagine the future, as some neurological patients do, often report a profound loss of self or purpose. It's as though the mental time machine's engine has sputtered, leaving them marooned in a kind of featureless present. We should also mention dreams. In dreams, our mind often wanders time and space freely, stitching together past elements and future anxieties in a surreal tapestry. You might dream of a loved one as they were long ago in a place you might go tomorrow, a mingling of times that only the sleeping brain can achieve so seamlessly. Dreams could be considered a form of involuntary chronesthesia, where our time traveling faculty goes on autopilot and explores scenarios uncontrolled by our waking logic. Sometimes, dreams even give the emotional experience of being in another time, like dreaming of being a child again and feeling those childlike emotions. Chronesthesia is not only about episodic memory, personal events, but also about our general sense of time. We can think abstractly, the Middle Ages were long ago, or the year 2100 might have these technologies. This is a form of mental travel to times beyond our personal experience. When you contemplate what life was like centuries before you were born, you're sending your imagination into history. Reading books or hearing stories can enhance this. Through narratives, we almost get to live in different eras vicariously. Or when you speculate about humanity's future, you mentally project forward on a global scale. Now, consider how chronesthesia relates to our earlier topics. The fact that you can vividly imagine the future is part of what makes time travel such an enduring concept. We simulate going to the future in our head with such ease that building an actual machine feels like the next step in some sense, and our memories of the past are so dear to us that the idea of literally revisiting them via technology is tantalizing. Our mental time travel teases us with a taste of what full physical time travel might be like. Perhaps this is why so many time travel tales revolve around personal stories, saving a loved one's life in the past, or seeing a future self. They resonate because in our minds, we do these things nightly and daily in thoughts. One delicate aspect of chronesthesia is how it can loop. Have you ever experienced deja vu? The eerie feeling that the present moment is somehow repeating, that you've been here before. It's like a glitch in your mental time awareness. One theory is that it's a memory misfire, where the current experience accidentally gets routed through the part of the brain that signals memory, so it feels like recall even though it's happening now. In a poetic sense, deja vu might be considered a tiny accidental time loop of consciousness. For a few seconds, your brain believes this present is also a past. It can be disorienting, but also fascinating. It reminds us how subjective our sense of time is. Some have fancifully wondered if deja vu is a sign of having lived this life before, or a crossover from parallel timelines. While science favors the memory hiccup explanation, the feeling of deja vu does hint at how our mind's time travel machinery can sometimes stutter, giving us odd sensations of time not being linear. Another introspective time anomaly is premonition, or the feeling of knowing something will happen before it does, without any obvious cause. Perhaps you think of someone out of the blue, and later that day they call you. Skeptics attribute this to coincidence combined with selective memory. We notice hits and forget misses. But in the quiet of night, one wonders, do our minds sometimes piece together subtle clues and project a likely immediate future scenario, giving a subconscious prediction that we then experience as an intuition? That's more plausible than true precognition. It would be our brain doing what it always does, imagining the future, but maybe more astutely than we realize, based on cues we weren't consciously aware of. In any case, these experiences show that our subjective flow of time and awareness can sometimes slip out of the ordinary groove. Chronesthesia is overall a gentle gift. It allows us to relive our joys, process our sorrows by revisiting them safely after the fact, and anticipate and shape what's to come. It's also a source of anxiety at times. Excessive dwelling on past regrets or future worries can rob the present of peace. In those cases, some mindfulness experts advise grounding oneself back in the now, essentially giving the mental time travel a rest. But when harnessed positively, mental time travel can be like flipping through a scrapbook of your life or drafting a vision board of your dreams. Used wisely, it can bring contentment and direction. As we lie here in a reflective state, we can practice a soothing exercise. Recall a pleasant memory in detail. What could you see, hear, smell? Spend some time there. Notice how your breathing and heart rate might change as if you're partly experiencing it again. Then let that go. Next, envision a peaceful scenario in the future, perhaps an upcoming lazy weekend morning where you have no obligations. Picture yourself sipping a warm drink, feeling completely relaxed. By doing this, you've just engaged chronesthesia, both backward and forward, and likely induced real calm in your mind and body. No physical time machine could be simpler or more readily available. In the next chapter, we'll wander into stranger territory, not just remembering or imagining, but the ideas of causal loops in consciousness. We will gently ask, could the mind ever get stuck in a loop of time? Might deja vu or certain mystical experiences hint at a looping consciousness? It's a speculative and dreamy subject, bridging psychology and a bit of philosophy. As always, we will tread softly, keeping a meditative tone. Our mental time travels so far have been under our control. Now let's explore what if time folded back on itself for the mind in less ordinary ways, all while keeping ourselves anchored in a safe and relaxed state. Causal loops in consciousness, dreams, deja vu, and the loop of existence. Now we venture into one of the more mysterious realms of speculation, the idea of time loops involving our consciousness. What would it mean for the mind to experience a loop in time? Could it be that in some enigmatic way, our thoughts or even our lives circle through events more than once? As fanciful as it sounds, people throughout history have reported odd experiences suggestive of loops, like intense deja vu, precognitive dreams, or a sense of reliving moments. We'll explore these gently as imaginative possibilities more than scientific fact and see how they connect to the broader idea of time travel. Consider deja vu first, since we brought it up already. Deja vu is the uncanny sensation that a situation is repeating, that you've experienced the present moment before, even though you logically know you haven't. It's as if, for a flash, your mind falls into a small time loop, giving you that I'm stuck on repeat feeling. While the prevailing explanation is a temporary glitch in how memory is processed, your brain mistakenly tags the current moment as a memory. Let's entertain a whimsical thought. What if, just perhaps, deja vu occurs because in some way you actually had been there before? One outlandish hypothesis from fringe time theories suggests that time might have tiny eddies or loops, and once in a blue moon, we go through a fragment of experience twice. Of course, this is not mainstream science, but it's a lovely thought for a drowsy, reflective state. In that view, a deja vu could be a sign that you are briefly in sync with a loop, the universe repeating a moment. like an echo in the canyon of time. People have often tied deja vu to more mystical ideas of life loops as well. For example, some interpret deja vu as evidence of reincarnation or past lives. Maybe you feel you've seen something before because a previous incarnation of you did, or that you dreamed the moment beforehand, a quick loop from dream to reality. None of these interpretations have proof, but they show our fascination with loops. We almost want to believe that time isn't a straight arrow, that maybe it has repeating patterns or cycles that occasionally surface into awareness. The concept of eternal return, that the universe or our lives might repeat endlessly, has appeared in various philosophies: ancient Hindu cosmology, the Stoics, Nietzsche's thought experiment. If, say, our life did happen countless times, deja vu might be a small bleed through of a prior iteration's memory. We're firmly in the realm of speculative philosophy now, but it's a soothing, circular idea to toy with while drifting off. The notion that time might be a wheel and we ride its spokes round and round. Let's turn to dreams and precognition. Many have experienced dreaming of an event or place, only to encounter it later in waking life, eerily similar to the dream. Sometimes these are chalked up as coincidences, or our mind's tendency to find patterns. Other times, they're incredibly specific and leave one wondering. For instance, someone might dream of a particular conversation or scene with odd details, and months later it unfolds in reality. Could this be a kind of consciousness loop where the mind dips into the future and returns with a memory? A more scientific view might say our brain is a prediction machine, and occasionally it predicts with uncanny accuracy. A more mystical view might allow that consciousness isn't strictly confined by time. Maybe in rare moments, it can glean something from beyond now. Retrocausality at the quantum level had us pondering signals from future to past in physics. Perhaps there's an analogous idea for consciousness, where information occasionally flows backward in time to manifest as a hunch or dream. There have been experiments and studies on presentiment, subtle physiological responses before a random event occurs, as if the body knows what's coming a few seconds ahead. The results are controversial and not widely accepted, but they're thought provoking. If any of it were true, it could suggest our conscious awareness mostly rides the forward wave of time, but somewhere deeper in our being, there might be a connection that can sometimes resonate with the future, almost like how you can sense a change in wind before weather arrives. Maybe our minds, at some subconscious level, sense a change in temporal winds. Another sort of consciousness loop concept comes from fiction and thought experiments. What if your life is a time loop? There are stories where someone relives the same day repeatedly, like the film Groundhog Day or many time loop tales. Usually, in these stories, the loop ends when the person learns a lesson or events are set right. Now, in reality, our days do feel repetitive sometimes, but not literally identical. However, consider if the universe were deterministic and eternalist. In a block universe, you could say we are always looping in the sense that your life in 2025 is permanently there in space time. And if consciousness somehow moves, perhaps after death, it could cycle back to birth. This is more metaphysical pondering than physics. A person like Nietzsche imagined eternal recurrence, that you will live your same life again and again eternally. Would consciousness be aware of that, or would each iteration feel fresh? Likely the latter, or else by the hundredth loop, we'd all have massive deja vu. But these musings can be strangely comforting or terrifying depending on how you see them. Comforting in that every joy and chance you missed comes round again. Terrifying in that every pain does too, unless you find a way out of the cycle. On a gentler note, think of daily or yearly cycles we do have. Circadian rhythms, seasons. These are loops in time that our consciousness is well adapted to. We wake, live the day, sleep, and reset. We mark years and birthdays, feeling a return each 365 days to a date. These are natural loops that give structure. They aren't causal loops in the paradox sense, but they create a feeling of looping within forward time. Rituals and traditions reinforce this. Every holiday might bring memories of previous ones, almost overlapping in mind. On New Year's Eve, as the clock strikes midnight, many feel the past year and the new year merge for a moment, a loop's closing and another beginning. One mystical concept worth mentioning is the idea of being stuck in time, or experiencing all time at once, a kind of loop or stasis. Some meditation practitioners, or people who had near death or profound spiritual experiences, report a state where time lost meaning, seconds felt like eternity, or they perceived a timeless unity. While not a loop per se, it suggests consciousness can alter its relationship to time dramatically. Perhaps in those states, one steps outside the normal flow, like stepping out of the river onto the bank, and sees the whole curve of the river at once. Upon returning, it might feel like you looped out and back in. Causal loops in consciousness might also refer to feedback loops of knowledge. For example, the bootstrap paradox, often discussed in time travel, information or objects with no origin looping in time, could have a mental version. Imagine you get a vivid idea for an invention after dreaming that future you came back and told present you how to build it. You then build it, and one day actually do go back and tell your past self in a dream. The idea had no origin except the loop. It's whimsical, but one wonders if some flashes of genius could feel almost like they were whispered to the person from outside time. Again, likely it's just brain creativity, but it's a fun scenario to consider. As we wind down this spiral of thoughts, it's important to note we haven't found any scientific evidence that consciousness can literally loop in time or send messages to itself. But contemplating it leads to a peaceful realization. Our mind is truly our time companion. It sits with us at the present campfire, but it can throw its light backwards and forwards, occasionally making sparks that resemble loops or weird reflections. Whether time turns out to be strictly linear or not, our experience of it is loopy, layered, and rich. We remember, we anticipate, we sometimes even feel like we are outside of time in brief, awe-filled moments. If you've ever been in a flow state or intense focus, time might have felt looped or irrelevant. Hours pass like minutes, or minutes drag like hours. That's a subjective time loop of sorts, where your internal clock disentangles from the world's clock. In a delightful way, we create our own loops by what we pay attention to. Perhaps that's the key. Attention is like the stylus on a record, and if it skips or moves, the song of time changes for us. With these musings, we near the end of our journey. It's fitting to conclude with something more grounded and yet enchanting: time travel in myths and ancient stories. Humans have told time bending tales for millennia. Before formal science, these stories were how we explored the dream of moving through time. They often carry wisdom or wonder that soothes the soul, much like our modern meditations on time do. So, in our next chapter, we'll quietly visit a few ancient and mythical instances of time travel, bridging our conscious loops with cultural ones. These tales, passed down through time, are a form of communication between past and future, our ancestors sending us imaginative messages. Let's listen to their gentle voices next. Time travel in myths and ancient texts, tales of ripples in time. Long before H.G. Wells wrote The Time Machine, people around the world were telling stories that bent time in surprising ways. These myths and legends carry a soft wisdom and wonder, often serving as metaphors for real experiences, like how time can pass differently in joy versus sorrow, or as cautionary tales about trying to change fate. Listening to these ancient voices, we feel a connection across time, a continuity of imagination. Let's visit a few of these classic time travel tales, letting each gently unfold in our mind's eye. One of the oldest written examples comes from ancient Hindu mythology in the epic Mahabharata. It's the story of King Kakudmi and his daughter Revati. Worried about finding a perfect husband for Revati, Kakudmi decided to take her to Brahmaloka, the celestial abode of the creator god Brahma, to seek counsel. They patiently waited for Brahma to finish a musical performance before presenting their request. Brahma laughed kindly and explained that time flows differently in different realms. In the short time they waited in Brahma's world, many ages passed on earth, specifically 27 Chatur Yugas, which is tens of millions of years. When the king and his daughter returned home, they found their kingdom completely changed and everyone they once knew long gone. Eventually, Revati married Balarama, a hero of a much later age, as Brahma advised. This myth strikingly anticipates the modern concept of time dilation. It's as if Kakudmi and Revati experienced a relativistic journey, coming back to a far future. The story conveys a sense of awe at the vastness of cosmic time and maybe serves as a gentle reminder. Be mindful of how you spend your time, because you might return to find the world changed. From Japan comes the beloved folk tale of Urashima Taro. Urashima was a kind fisherman who saved a turtle from some cruel children. The next day, a great sea turtle approached him. It turned out to be the same turtle, a messenger from the dragon god of the sea. The turtle invited Urashima to visit the dragon god's undersea palace as a reward. In that magical palace, Urashima met a lovely princess, Otohime, and spent what felt like a few happy days. But eventually, he grew homesick and wished to return to his village. The princess was sad to see him go. She gave him a jeweled box called Tamatabako, warning him never to open it, and sent him home on the back of the same turtle. When Urashima arrived back at his village's shore, everything had changed. His home was gone, the people were unfamiliar, and when he mentioned the names of his family, they only recalled those as people from long, long ago. He discovered, to his shock, that hundreds of years had passed while he was under the sea. Confused and distraught, he absent mindedly opened the forbidden box, and with a puff of smoke, he transformed into a very old man. The box contained his age, all at once. This poignant tale resonates with the emotions of time travel, the sorrow of outliving one's era, the price of venturing beyond mortal time. It also has a dreamlike moral: cherish your time, for if you stray too far from your world, you may not get it back. The Seven Sleepers legend, which appears in Christian, Islamic, and earlier variations, is another gentle time slip story. In the Christian version, set around the time of the Roman Emperor Decius, 3rd century, a group of Christian youths sought refuge in a cave to escape persecution. The emperor ordered the cave sealed. The youths inside fell into a miraculous deep sleep. Hundreds of years passed. The legend says they slept for 300 years, until the cave was opened again in the reign of a new, Christian friendly emperor. The youths awoke, thinking they had only slept one night. When one went to town to buy food, he was bewildered by the changes. Christianity was now openly practiced, and the coins he carried were antiques. Realizing a miracle had occurred, the townsfolk honored them, and shortly after, the sleepers peacefully passed away, their faith affirmed. In the Islamic telling, Surah Al-Kahf in the Quran, it is quite similar. Known as the people of the cave, a group of youths sleep for 309 years as a sign of God's power. This story, while couched in divine miracle, is essentially suspended animation, an early exploration of a time travel trope, cryogenic sleep in science fiction terms. It's comforting in these stories that when the sleepers awake, the world has become better, persecution ended. Time healed wounds while they skipped ahead. Perhaps the lesson is one of patience and trust, that sometimes retreat and rest can lead you to a brighter future. Another mythic theme is the time distorting power of the gods or fairy folk. In numerous cultures, spending time in a fairy or spirit realm leads to a Rip Van Winkle outcome. In Irish lore, for example, there's the tale of Oisin and Niamh. Oisin, a hero and poet, goes with a fairy woman, Niamh, to the magical land of Tir na Nog, land of youth. He lives there in Blas for what feels like 3 years. But longing to see his homeland and friends again, he asks to return for a visit. Niamh is reluctant, warning him that time flows differently outside their realm. She finally permits him to go, giving him a fairy horse and warning him not to dismount. Oisin returns to Ireland and is dismayed to find centuries have passed. The Fianna, his warrior compatriots, are gone, only legends now. While trying to help some men lift a stone, he falls off his horse, or the saddle in some versions, and instantly ages into a withered old man, the accumulated time catching up once he touches mortal ground. He lives just long enough to tell St. Patrick of the old days, bridging the mythic past to the Christian present. This story, like Urishima's, shows the bittersweet nature of time dilation in fairyland. Great joy and then great loss, highlighting how our mortal world moves on without us if we leave it for too long. These ancient stories often have a melancholic undertone. Time travel in myth is rarely for fun or casual adventure. It's an awe-filled and usually one-way journey that underscores the value of one's own time. The heroes often face loneliness or dislocation upon their return. Yet, there is also wonder. They got to see things beyond ordinary life, heavenly realms, lands of youth, divine counsel. Myths used time travel to emphasize moral points or the capricious nature of time. You can't get back lost time, Urashima. Virtue will be vindicated in the long run, Seven Sleepers. Don't assume tomorrow is guaranteed. Kukudmi's world vanished. Another beloved example is more modern folklore, Rip Van Winkle by Washington Irving. Though written in 1819, it has the flavor of an older tale. Rip, a kindly but lazy man in pre revolutionary American colonies, wanders off to the mountains, encounters some mysterious Dutch ghostly figures playing ninepins, drinks their liquor, and falls asleep. He wakes up, and 20 years have passed. He's aged. The American Revolution happened. Everything's changed, and his nagging wife has died. Rip's stream is almost a humorous reversal of the Seven Sleepers. He slept through work, through nagging, even through a war. It's both a funny cautionary tale about idleness and a commentary on how times can change. When Rip returns, he's oddly okay. He even benefits as the townsfolk enjoy his old stories. It might imply that sometimes missing the turbulence, the war, isn't so bad for a simple soul, though he has to adjust to a new era. King George's portrait replaced by General Washington's, for example. Rip Van Winkle has since become shorthand for someone oblivious to change. Even religious texts and folklore feature small time slips. In the Bible's Second Kings, there's a story where the shadow on a stairway goes backward as a sign to King Hezekiah, effectively a minor time reversal miracle. And folk tales abound, where people visit the fairy dance at night and emerge to find years gone, or conversely, they think they spent years away, but only an hour passed outside. These recurring patterns suggest a shared fascination. People sensed that time could be subjective, and they used stories to explore that feeling. For a farmer who goes to a festival and returns feeling like the day flew by, while his unattended chores now seem far behind, a time travel allegory expresses that. Or a person who experiences deep grief might feel that time froze for them, and when they rejoin life, everyone else moved on, akin to a seven sleepers metaphor. Listening to myths in this calm setting, we recognize that whether time travel is real or not, the emotions around it are very real. Longing for lost time, wishing to skip painful years, the dream of a utopian future, or the temptation to go back and change something. These are universal feelings given life in myths and fiction. As we near the end of our night's journey, it's comforting to know that our ancestors grappled with these same feelings. Through imaginative stories, they made peace with time's mysteries. We too can find peace by understanding that past, present, and future, however they flow, are part of a grand tapestry of human experience. We stand in a long line of storytellers and dreamers, all wondering about time. In our final chapter, we'll circle back to a more conceptual reflection, tying together science and myth, considering the philosophical implications if time could reverse entirely. It will be a gentle capstone, inviting you to imagine one last what if, a world where time's arrow flipped. Then we'll close our eyes and let all these threads of thought weave into soft dreams. Time's landscape and the endless allure of tomorrow. After traversing this lengthy road of speculation, we find ourselves back in the present, the only time we truly ever live in. We've peered into the depths of space and imagination, seeing how the flow of time might be rerouted, stretched, knotted into loops, or split into branches. We've seen that time travel, as a concept, is not strictly forbidden by the laws of physics we know. Relativity actually encourages a bit of time skewing to the future and leaves loopholes for the past if exotic conditions are met. Quantum physics hints that time may be more fluid and less absolute than our everyday experience suggests, perhaps even permitting some backwards influence as long as consistency is preserved. Yet, for all that, time travel remains elusive. It sits at the edge of our understanding, constantly teasing us. One moment, a new theory or finding raises hope that the door might crack open, like the idea of a stable wormhole or a clever warp drive metric. But then another insight or limitation steps in, reminding us of the enormous gap between theoretical possibility and practical reality. The energy requirements for most schemes, cosmic strings or Tipler cylinders requiring mass on galactic scales, warp drives needing perhaps the energy of an entire star, are mind boggling. The engineering challenges, constructing a wormhole or maintaining a super spinning object, are far beyond anything we can foresee mastering. And then, those pesky paradoxes, even if we built it, could we use it without unraveling causality, or would something always stop us? Stephen Hawking's playful question echoes, where are the time travelers? If a million years from now someone invents an actual time machine, might they not pop in to see us? Perhaps they abide by a temporal version of the prime directive, or perhaps they physically can't reach earlier than the machine's creation. Or maybe, just maybe, time travel to the past truly never happens in our universe. It might be that among the countless timelines that could exist, we live in one where history remains self contained, unvisited by its future. If that is so, it's perhaps a comforting thought. No need to worry about future meddlers or retroactive changes. We're cruising along on a stable timeline. On the other hand, if time travel is possible in some form, it forces us to broaden our view of reality. The universe might be far stranger, with parallel histories, or with a predetermined tapestry where every loop is woven in from the start. It suggests a universe where cause and effect are not linear, but part of a grand, interwoven pattern. Recall the Doctor Who quote about time being a big ball of wibbly wobbly, timey-wimey stuff. Thinking in this way can be almost spiritual. It hints that maybe the past, present, and future all coexist in some higher sense, and our consciousness just experiences them in sequence. Practical time travel may or may not come to pass, but the theories we've journeyed through serve a deeper purpose. They challenge our intuitive notions and force us to grapple with the fundamental structure of the universe. In exploring them, we've touched on relativity, showing time as relative and personal, on cosmology, the birth of cosmic strings and the fabric of space-time, on gravity at its extreme, and on quantum mysteries. In a way, time travel as a subject is a beautiful nexus of almost all fields of physics. It brings together the very large, cosmic, and the very small, quantum, the very fast and the very strange. As you prepare to drift into sleep, if you haven't already during this ultra long narration, consider this final gentle thought. The future is always being made, 1 second at a time. Every moment you live, you are traveling into the future at the steady rate nature grants us. Perhaps one day we'll learn to quicken that pace or take detours. Perhaps not. But even without fantastical machines, we are all time travelers on a one-way journey. This gives each moment its poignancy. In a world where time flows only forward for us, each experience is unique. Maybe part of the appeal of time travel is the desire to reclaim lost moments or preview what's to come. Yet, knowing what we know now, we might think twice even if we had the chance. Changing the past could be perilous, and seeing the future might spoil the surprise and struggle that give life meaning. For tonight, it is enough to dream. The theories we discussed will keep scientists and philosophers busy for ages to come. They may remain theories, or some might quietly transition into reality through breakthroughs. If you ever gaze at the stars and wonder if someone out there has conquered time, you wouldn't be alone in imagining it. Until we know for sure, time travel lives in our collective dreams, in stories, in thought experiments, and in hopeful equations scribbled on blackboards. The flow of time has brought us to the end of our expedition. Let your mind rest now, heavy with the wonders of cosmic possibilities. The river of time will carry you onward into a new day once you wake. Who knows what that tomorrow holds? In a sense, it will be a small personal time travel into a future you have yet to see. May it be a good one. And if your dreams take you wandering into the past or future tonight, travel safely and remember the gentle wisdom that the simplest way to visit the future is to live fully in the present. After all, as the old saying goes, time flies, whether we are having fun or dissecting paradoxes, and in the end, the journey is what makes it worthwhile. Sleep well, fellow time travelers of the mind.